non si vede dove? Qua? Ma sì che si vede, no?
Sì, ma da là non lo vedo.
Eh?
Da là non lo vedo.
Ah, ma io qualche volta ho visto quello.
Però si perde.
Sì, perché non abbiamo un mouse per... Vabbè. Ok. Spero che...
Sì, sì, poi tu sarai molto...
No, sì, l'ho visto nella colazione, gente, con questa opera, suppongo che non sta, che non
Good morning, everybody. We start now the first session for today. And this session will be focused on both experimental and theoretical studies of the interaction of anti-kaons with nuclei, and kaonic atoms. But before starting, it's my pleasure and my duty to thank the organizers for the beautiful afternoon and also evening we had yesterday while strolling through the streets of Prague and then listening to the concert and then this very beautiful place where we had our banquet. So thank you so much. Okay, and now let's say that we go to Italy, to Frascati Daphni, but not only actually. And the first speaker will talk about updated experimental insight into the strong interaction between anti-kaons and nucleons. Autumn, please.
Thank you very much. I also want to actually thank the organizer also for the whole week. That has been really a wonderful conference here and wonderful organization. And thank you to the audience for being here. First talk after the social dinner. Exactly. So this is an updated experimental insight, a bit biased because I'm going to basically talk about what I do, but you will see that there will be a lot of experimental information here. And we are dealing here with the K-Bareng interaction. So I think that I don't need to introduce the field at this stage of the conference. We know that Kn and K-Bareng interactions are very different. The presence of the strange quark makes so that the K-Bareng interaction has really special characteristics, strong coupled channel dynamics, the presence, strong attraction, and the presence of the lambda 1405. That we know there is a molecular state. We know a lot about one of the poles and a bit less about the lower energy pole. We have heard also about different theoretical approaches to the K-Bareng interaction. In particular, we heard a lot about chiral EFT, but there are other approaches. I put here a question mark on lattice because we didn't hear anything about lattice. There is certain inputs to the field from lattice, but there is we don't have a potential yet from lattice. They know how to handle meson-variant potentials with the inelastic channels, but probably for the next conference we will have also lattice to compare with our data. And it's obvious to say that the data is crucial to test, and in this particular case to feed the models. It was actually very nicely explained by Albert Feijó. When you go in chiral EFT from leading order to next to leading order, or you add more partial waves, you need new data, you need more precise data, you need data covering really different energies. And this is what we try to deliver. This is by Yuki Kamiya. I kind of vitaminated a bit this plot with different experimental inputs that we have in different energy regimes around the K-Bareng threshold, and I will be centering in these particular inputs: anti-kaonic atoms, femtoscopy, and kaonic nuclei. And I will start with the most precise measurement at threshold of the K-Bareng interaction that comes from anti-kaonic hydrogen. For those who are not familiar with anti-kaonic nuclei, basically you put a K minus taking the place of an electron, and in the excitation, in the X-rays of the last position of the last levels closer to the nucleus, you have a shift and a width that is, with respect to the electromagnetic value, that is caused by an attractive or repulsive strong interaction and the presence of the inelastic channels below the threshold. Siddhartha measured this energy shift and width with high precision. And actually this shift and width, in the case of kaonic hydrogen, you can kind of easily translate through this approximate Desser formula into a scattering length that is, this is the K minus proton scattering length, that is an average between the isospin 0 and 1 K-Bareng scattering length. And this was really the most precise, is still the most precise measurement at threshold. But I want to compare it here with the femtoscopy studies, because the measurements share a lot. And to this, I make use of this figure by Yamamoto-san. He actually used it for explaining psionic atoms, I guess, atoms with a psi baryon. And he shows how there is an overlap in our case with the Kelvin function with the nucleon potential, right? And from this, you see the effect of the strong interaction. This is the picture is very optimistic because we know that the distance actually between the K minus and the proton in the antichaotic hydrogens is around 10 times the Bohr radius. And we can directly compare with another picture that we have this week here from femtoscopy, that in this case is not exaggerated. This is basically femtoscopy in proton-proton collisions, small systems. For us, a small system is really meaningful because this small means that our sources, that is the mean distance between the particles that we detect and that interact is around 1 Fermi. And you see that you know that the correlation function, when we compare it with our data, we model it by basically this integral that contains the source and the interaction. And here you see actually the source, the small source of 1 Fermi, overlapping the nuclear potential. So you are really sensitive also to the strong interaction with femtoscopy. These two methods deliver different observables. On the one side, you have the shift and the width of the antichaotic hydrogen. On the other side, you have the correlation function. They can be compared with data, and they also can be actually compared together through some approximations. Okay? If we use these desert-type formulas and we use for femtoscopy the Letnitsky approach, we can compare a scattering length, the same scattering length of K minus proton that you saw before from Siddhartha. In the femtoscopy analysis in proton-proton collisions, we actually have also a good advantage when we study K minus proton is that we do in parallel the analysis of K plus proton. K plus proton is a rather well-known interaction, and we use it basically to constrain the radius, so the distance of the particles that we put in the correlation function. So this is a very nice input. A feature of this interaction and of this correlation function in particular, K minus proton, was shown by Kamiya-san, where you see that we have a huge influence of the coupled channels, of the inelastic channels. In particular, we have the K0n above threshold that is very visible in the data because you see a cusp. And also channels below threshold enhance the correlation function. These are the two main inelastic channels that contribute to the correlation function of K minus proton. And this is actually our K minus proton correlation function in proton-proton collisions. So very small systems, very sensitive to both coupled channels and strong interaction. And you see actually what I was saying, the cusp due to the opening of the K0n channel. And here you see that our data of ALICE is compared with the Kyoto model, and you see, well, good agreement, but also a good disagreement, right? So there is tension there. And the good thing is that we can also quantify the tension that we have here as a function of the influence of the coupled channels. And this is what you see in this plot here. Basically, as a function of the radius, so doing not only proton-proton collisions, but slightly bigger systems, we quantify what is the difference between what is in the model of the influence of the coupled channels in the models and what we see in the data. When you see a 1 here, means that data and experiment agree, and this happens actually for the sigma pi channel, but for the K0n channel, they do not agree. Actually, the data shows this more enhanced contribution from this coupled channel. And actually, you see it here in the comparison because the data is above the model. Then if we go to higher systems, in this case I show you this ALICE data in the same system, K minus proton femtoscopy, but in, the time goes, okay, good. I didn't spend 12 minutes, okay. In lead-lead collisions, where now here the size of the source is much higher, it's 9 Fermi. So compared with 1 Fermi, that up to 9 Fermi. Here the contribution from inelastic channels is expected to be negligible, and actually you see that the shape of the correlation function is rather different, right? Not only because of the higher radius, but also because of the much less influence of the coupled channels. And here again we compare with the expectation from Kyoto model, and we have an additional line. And this is Basically, through this fit that we have with this orange line is how we can compare actually with the values from the antikionic hydrogen. We do a fit of the real part and imaginary part of the K- proton scattering length, and the result is what you see here in red from ALICE in lead-lead collisions compared with this pink line that is basically Siddhartha. So you see that really the level of precision that we achieve is already comparable with what antikionic hydrogen can deliver. So we have very good data for K- proton, right? What we don't have is very good data for K- neutron. We can basically not access that experimentally, so we try to access K- deuteron, where the nucleon is inside the deuteron, of course. This is very helpful because you saw that the K- proton scattering length is basically a mean average between the isospin 0 and isospin 1 component. In the case of K- deuteron, the isospin 1 contributes with much higher weight. And the experimental constraints that we have in this sense here up to today are very, very weak. That's why we are basically repeating the experiment of antikionic hydrogen with deuterium, in this case, antikionic deuterium. It is now currently taking data, and you will hear in the next talk by Johannes Smerkal about this. It's a very challenging experiment because the yield, that is to say the yield of X-rays from the excitation of the levels that we are interested, the lower levels, is much more reduced than in the case of keonic hydrogen. So it's very, very, really complicated measurement. And also the interpretation of this result also requires some effort from the theoretical side, because now you really need full three-body calculations. It was shown yesterday by Tetsuo Hyodo, to calculate the shift and the width of the antikionic deuterium. Here, the CERTIFE formula are not precise, so you need really the full calculation, as was shown by Hyodo. We try to access also the isospin 1 interaction, K-bar N interaction with ALICE, with femtoscopy. At the first moment, we have already preliminary data of K0 proton, K0 short proton correlation that you see here. The data is less precise than in the case of charged particles, obviously. But here, we already have a sensitivity of the influence of the K-bar N in isospin 1 interaction. Basically, this correlation function, the theoretical one that you see here, comes from two different potentials, one of the K-bar N and one of the K, so kaon nucleon that is well-known and constrained. And, okay, yet this is what you see when you don't have really, really precise data, that everything is fine. And even when we don't have still a good knowledge about this channel here, everything goes well with the data. So we want to be more sensitive to this isospin 1 channel, and we are basically doing the same game that we did before, K- proton from Siddhartha, antikionic hydrogen. We will do K plus D and K minus D femtoscopy with ALICE in small systems. We are working on it, and probably in the next few months you will be hearing about this. We are also training ourselves, and we have already very good results in femtoscopy with deuterons. This was presented by Babani, and also we had the data from that in heavy ion collisions by STAR, where there you really have to deal with an extra effect, that is how is this deuterium formed in the nucleus-nucleus collision, whether if it is created via coalescence or other mechanism. So I hope that you can hear from this in the next month by this K- deuteron femtoscopy. Okay, since we are speaking about the deuteron, K- deuteron, we are already in the three-body case. I move now to the keonic nuclei. First, I do a first stop with the Amadeus data. This will be also shown in this session, so I will just flash it. This Amadeus data basically deliver very good data in absorption experiments, K- absorbed in 12 carbon or for helium, and it delivers this invariant mass spectra of lambda proton, also of sigma 0 proton, that it was actually crucial. It was the experimental data that was crucial to show how in these absorption experiments really possible signals of chaotic bound state, you are not going to see them because you have all these lines here, and these are not chaotic bound state. These are multinucleon absorption. And this data is actually used for delivering data below threshold and above threshold, and you will see it from Christian in the next talk. What we do have now that it looks more promising is the data from JPARC. You also heard from this. It's a K-minus beam of 1 GeV in a helium-3 target, and the lambda proton that is coming out of this reaction is detected. And it is this spectra of invariant mass is currently interpreted by E15, and also by very similar interpretation by theoreticians with a quasi-free background and a signal that could be this quasi-bound state with binding energy of 40 MeV and a really large, unexpected in some sense, width of 100 MeV. They also deliver this spectra that I will use in a second. That is basically this QX is the momentum of this intermediate kaon there. So it is by detecting the momentum of the lambda and the proton, you deliver this spectra, and in red you see the momentum of the part that is fitted to contribute from the K- proton-proton. And I will use this spectra in a second, trying to interpret also this data of the three-body femtoscopy. It has been shown by Laura that we are now also in small systems in ALICE, we are analyzing three-body correlation functions. And what we do here is build a correlation function in function of Q3. So we take the correlation of the three particles, and using the Kubo method, basically what we do is to obtain this cumulant. This cumulant is nothing that what is left of the correlation function once you subtract everything that is connected to two-body interaction. And all these terms that are connected to the two-body interactions, we know very well because we obtain them experimentally at the same time. We subtract them, and we see what is left in this three-body correlation function. And what is left when we look at proton-proton K- cumulant is this, that is basically nothing. So it's compatible with zero. Basically, this tells us that there is nothing else there than two-body effects. And this is actually nice if we compare again with this momentum spectra from E15. If we look at the region of the momentum of this K- proton-proton, that is here around 0.4 GeV. This translates in our map of the cumulant about more or less in this region that you see here marked in blue. And again, here we are really sensitive. We have good data, and again, there is nothing there that we can see that is more than two-body interaction. So probably for the description of these systems, like it is done currently, you don't need any other thing that is two-body interaction. But we have other cumulant. We have also proton-proton lambda and proton-proton-proton. And actually, in the proton-proton-proton case is the only case where we actually see a deviation. So in this cumulant, again, we remove the two-body contribution, and we see something else, whatever it is, if it is a Pauli blocking effect, if it is final state interaction in this very low relative momentum that could be compatible with some interaction. And again, we have calculations nicely shown by Nina Sevchenko of chaonic clusters with more nucleons, so K bar N and N, where there we already have three baryons. And we cannot say if this is relevant still or not for these calculations, but one has to really keep in mind that we, in these cumulants, we saw something else than just the two-body interactions that are used for these calculations. And basically, I am done. I just want to show here a very, very brief summary of the data that was shown during this week. Really, it was really impressive, the quantity of new data in Hyperon systems, but also in K-bar systems. We have had this preliminary data also from JPARC now with a 4 helium target in K- in lambda deuteron invariant mass. We had data that is used for the first time when we increase the number of partial waves in chiral EFT analysis shown by Alberto Feijó. That is also connected with experimental proposal at JLab. We will have, and we will see in this morning session, new data from LUX in photoproduction below threshold. And we have had also proposals of looking for new data in different systems in order to pin down better the contribution of the lower pole of the lambda 1405. So overall, really, we are in a moment where a lot of new data is arriving. I think that this could be really a boost for this investigation, like it was the publication of the Siddhartha data with the most precise measurement at threshold. And we are still on the search of a description of the K-bar interaction that really covers the whole energy range and all the physics phenomena that we have there. So in order to achieve that, you really need to eat all the cookies and use all the data. Thank you very much.
Thank you very much for this very comprehensive talk. Time is open for questions or comments. Apparently everything was completely clear or already known maybe. But okay, there's one question there.
Thank you for the nice talk. Would you please go to page 18 on the K-short proton correlation? In the case of K-short, everything is corrected for the, how to say, the pair purity or some other jet contribution and something like that.
Yes, there is still, I think, some and this is preliminary data, this is still some indetermination in the determination of the radius. Here, here you don't have in parallel, it's not as, we don't have this advantage that we have in K minus proton, K plus proton, where you do the two analyses contemporaneously and you have the determination of the radius from K plus proton. So there is still a determination of the radius that is also reflected in this width of this theoretical band here. But yes, the feed down contribution, I guess, they are.
In the case of this K-short proton correlation function, then we can use the scattering amplitude itself. Many people have the scattering amplitude, but not to the potential. In the case with the Coulomb potential, then it's not easy to include the Coulomb potential effect into the correlation function. But in the case of the charge neutral pair, or Coulomb-less pair, then we can just use the scattering amplitude available from many authors. Therefore, we can use the combined correlation function without using the potential.
So you think that just using the correlation function will be as exact in this particular case, since we don't have a Coulomb, as using the potential that we plug there?
Yeah, in this case, we believe that this is a good combination and our favorite, and Kamiya-san calculated it, I believe. But now it is your size, and you can collect all the available Kn and K bar N amplitude from all over the world, and put them and compare. You can do it. Then that's the first time things to do, I think.
Yeah, thank you very much for the comment. It's actually very, very nice system because it's actually one of the components you know very well. But yes, obviously the sensitivity that we have in this kind of data without that is not charged particle and charged particle is much
and many hadron physicists do not like correlation function because we have to go through potential. But they have the amplitude, but it's not.
Yeah, we can compare with more models.
To construct the potential. Therefore, you can appeal this.
Thank you.
Are there other questions or comments? Short questions or comment? No? So let's thank the speaker again. And let's move to the second presentation by Johannes Meskel. He will talk about kaonic atoms, status, results, and plans.
Thank you.
You're welcome.
Okay, good morning, everybody. It's a pleasure to be here. Let me first, of course, thank the organizers to inviting me here to give this talk, but also for the excellent work they have done during the conference. And I think we enjoyed all very much this nice event yesterday evening. Okay, I will try to talk about kaonic atom status, result, and plan. And I will give you an overview of the experimental parts of kaonic hydrogen and also kaonic helium performed in the last 20 years. And if you need, you want to know more, you can look at the review of modern physics, which I have published shortly, the modern area of light kaonic atomic atom experiments. So you'll find a nice compilation here about the work which was done in the last 20 years. Okay, the motivation I can keep pretty short. It was discussed quite often during this conference. We are using exotic atoms, trying because the mass of the kaon is much higher than the electron, so it comes much closer to the proton, and we can have observable energy shifts, and also we can measure the decay width, and so we have access to the scattering lengths at zero energy, and this can be then analyzed systematically and explained in the framework of low-energy effective field theory. Just a short catch, what happens if we have a hydrogen target, what happens, we shoot kaons into the target cell, it's slowed down and finally will be captured by rejecting the electron, and because the mass of the kaon is so high, so it's not in the ground state, but it's in an excited level, and then it has to cascade down. And during this cascade, you have different processes. And one of the main processes, which is not so nice for us, is the Stark mixing, because it's mixing the L states, and so it can come closer to the lower L states, and then you have nuclear absorption. So that's, if the density is too high, we get less kaons coming to the ground state, and this is something which we have to take into account, not to run at liquid hydrogen density, which would be, of course, nice, because then we can stop all kaons, but then we would have no X-rays in the ground state. And what we are doing, we just measure the X-rays coming down to the ground state, 2 to 1, 3 to 1, 4 to 1, and then by subtracting the pure electromagnetic values, we get the energy shift. Because we need kaons, I just want to have shortly introduce the two main facilities where we can do the experiments. One is Daphne and the other is JPARC. Daphne is an electron-positron collider where you just produce electrons and positrons just with an energy which is giving you exactly the mass of the phi. So the electron-positrons collide, producing a phi meson. This phi meson is produced more or less at rest, and it will decay to 50% in a K plus, K minus. And there we get a monochromatic kaon beam, which is, of course, quite nice if you want to stop the kaons in a low density gas. The other system is, of course, much bigger. It's the Japan Proton Accelerator Research Complex, JPARC, where you run with a primary beam of 30 GeV protons. The protons are shoot on a gold target, and then you can also produce kaons. But in that case, the kaon momentum is in the order of 1 GeV over C. So this is the main difference. So in Frascati, we produce much less kaons, but with a very low momentum range, more or less with monoenergetic kaons, while at JPARC we have high energetic kaons, which are, of course, then much harder to stop in a gas. So let me just go now to the status of the kaonic hydrogen. I will start with the pioneering work, KPX, and DIA, and then just tell you something about Siddhartha. Before I just go into the details, I just want to show you that the success of the following experiments also strongly depending on the detector development. As you can see, we started with the KBX with lithium drifting silicon, which has an energy resolution in the order at 6 kV, the order of 400 electron volt. Then for DIA, we used charge-coupled devices. It's just similar to a photoemulsion, which you just expose the CCDs, which you have, you might know, everybody has it in a cell phone for making pictures. And this was the first CCDs which we developed for this experiment, which was able to also because of this high depletion depths of the silicon charge-coupled devices, to really stop efficiency X-rays in the energy range of 5 to 10 kV. And the main advantage of that is that with this detector, if you have an X-ray, you have a single pixel, while if you have charged particles or gamma rays, you get a bulk of pixels, so you can easily discriminate between X-rays and gammas. And finally, we were going to develop silicon drift detectors. For the Siddhartha experiment, we just developed large area silicon drift detectors with 1 square centimeter, and we had 3 cells on 1 wafer. And this was the success, I think, of the experiment, to have this nice detector running for the Siddhartha experiment. Going a step further to go to the DIA measurement, we had still some problems with this type of detector, so we could improve it. And this is the STD, a silicon drift detector with some cube amplifier, which I will show you in a second. So these are the 2 experiments. I just want to show you roughly. It's the E228 at the KBX at KEK, and the other is the DIA experiment at Daphne. So with these 2 experiments, we just get very nice results, and here are the results of these 2 experiments, and they really could solve the chronic hydrogen bustle, because the old experiment all shown an attractive type of reaction, while also the scattering experiments were lying in the order showing that this shift should be repulsive. And this was then finally confirmed by KPX and also by DIA. Let's go now to the next experiment, which is Siddhartha. Here you can see a sketch of the experiment. And the main part of the Siddhartha experiment is a cryogenic target cell, which is running at 25 Kelvin, and with extremely thin sidewalls, so that we are able to collect the 6 kV X-rays without getting too much absorbed in the cell, in the sidewall. And we use these new developed silicon drift detectors with an energy resolution in the order of 160 electron volt and a drift time below 1 microsecond. So this was essential, as I will show you in a second, for really for suppressing the high background which we get during the within Daphne. And here you can just see a sketch how the machine is working. On the left side, you see the blue line is when Daphne is filled with electrons. It's filled with electrons roughly to 2 amps. So 2 amps are running around in one ring, and then the positrons are filled also almost to 1 amp, and they are running in the other direction, and then you have an interaction region. And here we produce the phi mesons, as you can see, and we have 2 scintillators where we can just simultaneously measure the K plus, K minus, so we get a good knowledge when the kaons are going into the target cell, And with the silicon drift detector, we have also timing, so we have triple coincidence to really strongly suppress the background. And this can be seen here quite nice. On the left side, you see just the diagrams. The first diagram is just a calibration run, and the second, what you can here is, what you can see here is what happens if we run without coincidence. And you see the background is high. You have to scale it by 10 to the 4, and if we just ask them for Keon coincidence and for a coincidence with the silicon drift detector, we can suppress the background by almost 4 orders of magnitude. And this is really essential. And here you can really see this was a Keonic helium experiment. Here you can really see the peaks are coming out. You don't see the peaks in the middle spectrum. They are there, but because the background is so high that you are not able to see it. And doing that, we were able to perform this Keonic hydrogen measurement. Here you can just see the final spectrum, background subtracted and fitted, and the K-alpha peak is really shifted from the pure electromagnetic value, which is clearly seen. And the Siddhartha experiment is the most precise experiment up to now. And here you can just see the results of KPX, DEER, and Siddhartha. And of course, this gives also some important information for theory. So these are the different theoretical prediction constrained by the Siddhartha value. If you do the same for k minus n, you see there is quite a difference, and that's the reason why we plan now to measure also Keonic deuterium to get a handling on the k minus n amplitude. So this brings me to the way towards Keonic deuterium. I just will only tell you about Siddhartha II at Daphne. There's also some work going on at JPAC with E57. We have already some hydrogen pilot run, but we found out that we still have to improve quite a lot to perform the experiment at JPAC, which is just going on now. But let me just show you the Siddhartha experiment. And first of all, why it's so challenging to measure Keonic deuterium. You see the X-ray yield is expected at least to be an order of magnitude less. And the 1s state should be even much broader. And so that's the reason why we have to really update it and improve our Siddhartha system with extra V2 counters to discriminate about asynchronous background that we can do due to timing, but synchronous background we can only do to the spatial correlation. So let me point out what we expect with one inverse picobahn. We expect to get roughly 2 counts, and what we are getting now from Siddhartha, from Daphne, from the machine, roughly 3 inverse picobahn per day. So we expect 6 events per day and an enormous background. And so this is what we have to fight. We have really to fight against this background, and this we have tried to do as good as possible. Here you can just see the setup in the center, the STDs, which are just surrounding in almost 2 pi geometry the cryogenic target. And then we have placed a first V2 counter, V2-2. There we can then reject charged particles which are produced due to absorption coming from the K absorption by the deuterium. And here we can just reject particles which are going to the STDs, producing similar events, deposit similar energy as X-rays in the STDs. With V2 we can get have a good timing correlation, so there we can also just drastically improve the background situation. And here just we have developed, as I said before, we have developed new STDs. So these are 8 cells on one wafer, and the cell size is now a bit smaller, so that we have a much better timing resolution, and the energy resolution is, as you can see, very nice. And on the other hand, also due to this new cube preamplifier, which is just this small dot on the backside, you can see. You can see here, this is the amplifier is less than 1 cubic millimeter and is bonded to the anode of the STD, and this gives us an excellent energy resolution, and it's much more robust against high count rates compared to the silicon drift detectors which we used in Siddhartha. And this will be the Monte Carlo simulation of what we should expect with 800, roughly 800 inverse picobarn. We put in a shift of minus 800 electron volt and a width of also of 800 electron volt. The detector area is increased compared to Siddhartha almost by a factor of 2. And so this is what we would like to get if we get enough kaons. We will achieve a precision if we can, if the predictions are roughly in this area, what I said, width 800. We get a precision and shift of 30 electron volt and the precision, the width of 75 electron, which is comparable with the Keonic hydrogen measurement. So this is the red rectangle is the targeted precision, and then here you can see the different theoretical prediction, and I think with that we can just give a hint to the theory and help to provide information what can be improved. And the nice thing is, I can tell you, we are just running now. We have deuterium in the target cell. We just started beginning of June. I cannot show you the deuterium spectrum, but I show you what a test spectrum, which were done during beam tuning in April, May, with helium, and you can see the region of interest, and at around 7,000 eVolt, so 7 kV, we expect a peak. With helium, you see there's a flat background, so there is no structure in between, so that's quite helpful for our determination then of the final measurement. Now, I just want shortly flash about the Keonic helium experiment. There was in Keonic helium, you cannot go down to, you cannot measure the 1s level because the absorption is so large that you have only access, at least in the moment, to the 2b level, and the width and shift is of course pretty small. But if you look at the old experiment again, there was they measured an extremely huge shift in the order of 40 electron volt. Which we showed with the KK experiment and Siddhartha data that that's not possible. The shift is close to 0, and this is also what could be explained by theory very well. Now there is a step forward, also detector development, which was performed at NIST, that's the National Institute for Standard and Technology. That's the TESS spectrometer. It's transition edge sensor. It's a polymeter which is running at 70 millikelvin, and of course you get an excellent energy resolution. But of course the intrinsic efficiency is much smaller, so you have only small pixels. But nevertheless, this is in principle how such a sensor is working. You have an absorber where the X-rays are depositing their energy. It warms up a bit, and then you are running on the transition edge, and you can just determine very precise the resistivity, and this gives you then a resolution in the order of 5 electron volt at 6 kV. I'm almost finished. At 6 kV. This is 5 electron volt you have to compare with the silicon drift detector of 150 electron volts. So this is, of course, a much bigger advantage. And here, just the results. And so these are really impressive. You can just get the statistical error of 0.4 electron volt and the systematic error of 0.2 electron volt. Roughly the same for both helium-3 and helium-4. And now let me just show you the results. Here, just on the top, you see the E62 experiment with the TESS spectrometer. You can just see the very nice thin lines compared to the Siddhartha experiment. And here, just you see the very nice result of the E62. Okay. Just an outlook, what we can do at Frascati in the next year. I think the interesting would be determination of the charge kaon mass, even with a Fox's spectrometer or TESS. And with that, let me thank you for your attention.
Thank you for this complete overview of kaonic atoms. Are there questions or comments? I would have one question. It's more a curiosity, but how long will you be able to take data at Daphne this time?
Okay, we hope that now there's a summer break. Because it's getting too hot, so the machine has to stop. Then there's some beam tuning and some experiments until end of the year. So we should run the whole next year. So that's, the idea is to start January or February, and then we run as long as we can.
So
we can just get
the integrated
700
luminosity?
Integrated luminosity of 5 to 700 in Verspi-Kurbana.
So you should have very new results.
And then, of course,
Interesting results.
we hope to get some good results out of it here.
Okay. Are there other comments or questions? If not, we thank the speaker again.
Thank you.
And we move to the third speaker, Christian Pichicchia, who will talk about low-energy kaon-nucleon interaction studies by Amadeus.
Thank you. So let me warmly thank the organizer. The conference was really perfectly organized. It's a great pleasure to be here. I hope you can hear me. So I flash on the theoretical background because colleagues introduced it much better than I could do. I'd just like to stop a second on the present status, which was also shown by my colleagues for what concerns the sigma 0, pi 0, and lambda pi 0 channel, which will be the main topic of this talk. And just a few comments. Obviously, we well know that we really need some more data just above the threshold. And also, I would like to stress that the data which we have available, these 3 points at some 100 and something MeV of the kaon momentum in the lab, are not really two independent measurements. So here, a total cross-section for the lambda sigma pi was measured, and then the two channels were disentangled based on some arguments, which can be isospin symmetry, total energy of the measured lambda pi channel, but really a separated independent measurement of the two channels is needed. And at the end, I will also comment something on the momentum resolution of the kaons. So again, very briefly, if we move to the isospin 1 sector, Here we have a summary of the SU3 coupled channel results. You see that we have an even bigger spread of the predictions in the S-wave sector. And as we heard, obviously we are awaiting for the Siddhartha 2 results, which will constrain these models at the threshold, but I would like to remind also that we already have an experimental result below the threshold, which I will remind briefly. So Amadeus in general is dealing with the K- low energy interaction with nuclei, but today I will mainly focus on cross-section measurements when a K- interacts on a single nucleon, on multinucleons, and briefly, very briefly at the end, I hope I will have time to show some perspective onto the sigma 0 single and double nucleon cross-section future measurements. So you heard how fantastic is this beam, which we take advantage, delivered by Daphne. So we have these almost monochromatic K-, which start with an initial momentum of 130 MeV, but then the cross-section, which we measured, is at around 100 MeV because they are a bit degraded by the materials. Which materials? So what we analyze are the data which were collected, or we collected together with the Chloe collaboration. Chloe is this simple but amazing detector, is a big drift chamber for the trucks, surrounded by a calorimeter, which we use for measuring the energy deposit, essentially, of the protons and the photons, what we call clusters in our jargon. It is almost for pi acceptance, and what we are doing is to use it as an active target. So we measure the K- absorptions in the materials of the detector itself, which means carbon in the solid wall of the DC and a mixture of gases from the DC inner part. This mixture is mainly helium plus carbon and hydrogen, which are all together in the isobutane molecules. This fact is not trivial. I will maybe comment if I have time. And also, we have almost 50% of absorptions at rest and 50% of absorption in flight, the interesting in this talk today. So the kaon directly hits the nucleus with a mean momentum of 100 MeV. So you see, this data is really a mine of information, but to extract this information is at all not trivial, because you have to imagine that all these targets and the rest and the flight are all together in our raw file of data, and we have to disentangle all these components. So let me start with the K-n, so the isospin 1 S-wave measurement. Here the challenge was to disentangle the direct production of the lambda and pi, which can occur both S-wave or P-wave through the formation of the sigma 1385, from a copious background which comes from the primary formation of a sigma or lambda hyperon, followed by both elastic or inelastic final state interactions, and this gives rise to this highly uncorrelated part of the mesos versus the hyperon scatter plot. So the first step of almost all of the analysis which we perform is the determination of the recognition of the lambda through the decay into a proton and pi minus. And the main background of this vertex is due to the three-body decay of the kaon. So obviously you have to recognize the proton very precisely, but unfortunately it's not enough to measure a proton in a calorimeter. Why? Because you would end up with these protons, so you would lose all those low-energy protons, about less than 20 MeV in energy, which are completely absorbed in the first layer of the calorimeter. So what do we do is to tune this selection in the dEdx versus momentum plane, which is done taking into consideration the protons which are recognized by energy in the calorimeter, and then we apply to all the positive tracks which have the last hit near the calorimeter. You see that we can very well disentangle the protons from the pions, for example, and we end up with this very nice invariant mass shape of the lambda. In lambda pi, then we have to further associate another pi minus to the interaction vertex, to the hadronic interaction vertex where the K minus is captured. And okay, the philosophy of the analysis is to perform a multidimensional fit, but let me show you what's the meaning of the fit. The meaning in this case was to disentangle the P wave, the sigma 1385, from the S wave, the non-resonant formation, the non-resonant is just a wall below the energy threshold of this channel. We are in helium, so around 1412 MeV. So from the measurement of this yield, we succeeded to extract the non-resonant transition amplitude, the S-wave isospin 1, which can then be compared with the prediction from the various SU3 coupled channel models. So the same now we wanted to do into the sigma 0, pi 0, and lambda pi 0 channels to measure the cross-section, which means that we are looking for K- absorbed on a hydrogen from the isobutane molecules, very complicated, in flight, so at a momentum of 100 MeV. So the first step, obviously, is to recognize and to disentangle the photons. So first, for example, in sigma naught pi naught, you have to pin down 3 photons. These we do by time of flight. And then we disentangle by a combined square, taking advantage of the 2 invariant masses of the pion and the sigma. You can see that we end up with a very clean sample of pions and sigmas. This is a 3 sigma cut around the nominal values, and this is the phase of our neutral pion and our neutral sigma. So at this stage of the event selection, you end up with some signal. You will immediately understand why this peak is the signal over a huge background. So the signal is, again, K- hydrogen hyperon pion in flight. Obviously, you will have the background of the same reaction at rest, and then a mass of background due to K- absorption on a bound proton in helium or carbon with the same final state. Further, you will have all the elastic and inelastic final state interactions in the nuclear environment. And furthermore, in lambda pi 0, all these backgrounds are copy-pasted when you primarily produce a sigma 0, and then this decays into lambda gamma. So how can we enhance the signal over background? Luckily, the signal in this case have a very simple and straightforward kinematics, because the kinematics is closed by energy momentum conservation, which means, here I show you Monte Carlo reconstructed inside the detector, scatter plot of the meson versus the hyperon momentum in the 2 channels. They are extremely almost back to back, and you can pin down by a phase space cut the signal. In the lambda pi case, which is the more critical, you have one more gun. You know that the momentum resolution in the lambda is much better than in the sigma 0. You can imagine the sigma 0 has a photon, so the resolution in the momentum is order of 10 MeV. So this is the angular correlation of your signal. By cutting on the angle, you really get rid of the nuclear absorption processes. So this in black is the phase of the final selected events, and this is the signal. I tell you why. You see how you can enhance the signal. Why is the signal? Because again, momentum conservation means that if you feed the total momentum of hyperon pion, you have to resemble the original momentum of the kaon. It's just momentum conservation. So this peak here is in sigma 0 pi 0, the conserved momentum of the kaon, 100 MeV. What is this? Obviously, the nuclear background is more or less the Fermi momentum of the absorbing nucleon, okay? So we are lucky, by the fit we can disentangle. You see in sigma naught pi naught, the very enhanced signal of K- hydrogen over this broader nuclear absorption background, and even higher signal over background you can obtain in lambda pi 0. So by these, we ended up with the measurement, first simultaneous measurement of lambda pi and sigma pi of the cross-sections. So our measurement is this blue point, which I compare with the bubble chamber results. I put over the calculation by Professor Sikida, Hyodo, and Weise of 2012. So first message, you see that the precision of the measurement is much higher with respect to bubble chamber. So let me comment a second. You also have to take into account for the resolution in the momentum of the kaon. So, okay, in our case is slightly better, but this resolution has also a different meaning with respect to bubble chamber, because in bubble chamber what they do they have a spread momentum of the kaon in between 0 and 300 MeV, and they just slice this momentum in pieces, which means that the momentum distribution in this range, which is quoted here, is to be considered flat. The momentum distribution in our measurement is a Gaussian. And I think that this should be also taken into account in the theoretical fit to the experimental data. Okay, so the paper is ready, we will submit soon. Obviously, the next step would be to extract the phase of the lambda 1405 from this almost isospin 0 channel and, in the invariant mass. What's the problem? My argument is very simple. So if you absorb a K- on a bound proton in carbon, you have an invariant mass threshold, which is nothing but the separation energy of the proton 1416 in carbon. But if you use flight kaons, the 100 MeV momentum of the kaon traduces in 10 MeV in invariant mass, which opens the window to the higher pole of the lambda 1405. So this would be really a nice way to see the higher mass pole of the lambda 1405, but unfortunately, the good of the previous measurement, the presence of hydrogen, is the mess of this measurement, because you have to get rid of K- absorption on hydrogen, which is obviously non-resonant and is just some structure here around 1430, 1440, depending on the momentum of the kaon. Let me show you, we already performed this in sigma plus pi minus. Here the situation is different because taking advantage of the good resolution for the charged hyper and pion momenta, you can really disentangle the rest capture, the flight capture. Look how interesting is this flight sitting around 1412 MeV from the copious background of K- hydrogen interaction. But obviously for the theoretician, the interpretation of the spectrum is much more complicated because you have the contribution of the isospin 1 and the isospin interference terms. So I jump to K- multinucleon cross-sections. We learned very well that K- multinucleon is very important. Even if you don't take into account in the optical potential, you cannot even describe the kaonic atom data. And Otan already showed you that we measured the branching and the cross-section both in lambda proton and sigma 0 proton. This is a summary of all the branching ratios for the 2 and 3 nucleon absorptions and the corresponding cross-sections. And these were also already interpreted in terms of chiral model by Jarka and Angels. Also, we extracted the total branching ratio for the quasi-free 2 nucleon absorption process, and also comparison with the chiral theory can be found in this reference. Otan mentioned that we don't see any evidence for bound state. This is not in general that the bound state does not exist, but the message is that it cannot be highlighted in K- induced reaction at this low energy in a light nucleus. And the reason is very simple. The reason is that in this case, it completely overlaps with the 2 nucleon absorption because the nuclear form factor is dominant in this channel. So you would see a signal of a bound state only in realistic case, it would have a very narrow width, which is not the case, as we know. So even by selecting the back-to-back production with the same cut, which was also previously applied to the Finuda data, we can completely describe our spectrum in terms of multinucleon absorption processes in very well agreement with the work of Maga, Sozet, Ramos, and Toki. So I conclude with the last measurement. We also measured the 4 nucleon absorption cross-section for the first time. We absorb kaons on helium, and we look at the golden channel, lambda triton. Very few events exist from bubble chamber, 40, very nice measurement from Finuda, but here the global, not the 4 nucleon absorption yield was measured. So we measure tritons by measuring their mass by time of flight. You can see what a nice signal of tritons we have here. And again, the kinematics is the key point. The analysis is very simple because in 4 nucleon absorption, the invariant mass of lambda triton is the highest possible. And given the excellent resolution in the lambda triton invariant mass, we can separate the rest capture from the flight capture. You see this discriminant in red. And this is what we did. So this red distribution can be just explained by flight for nucleon absorption of the kern from which the cross-section. The same analysis we also repeated in carbon, where we have a higher statistic by using the alpha-like bound helium, and we also obtained the same cross-section for the sigma triton channel. So if I still have a minute, one perspective, and this is a message to ask for your help and your collaboration. We could really measure the cross-section of sigma 0 single or double nucleon absorption, what we suggest by absorbing a K- in for helium and looking for the primary 3 nucleon absorption ending in sigma 0 D with the neutron as a spectator, and then looking for final state interaction of the sigma 0 on the neutron or on the deuteron, so 2 and 3 body interaction. We did a very preliminary comparison with data not in helium, in carbon, pure carbon target. Obviously, the measurement in helium would be much cleaner, and it's mandatory. And just to show you, so this is the calculation of the invariant mass. Again, the invariant mass is the highest that you can obtain, and is here, is right here. So what we expect is the final state interaction deforms a bit this distribution, giving rise to this part of the spectrum. This one is the 2 nucleon. I have no time, but if you are curious, I can show you. And at what momentum of the sigma you measure this cross-section? At a very narrow 500 MeV. This is the calculated momentum of the sigma when emerging from the 3 nucleon absorption, and you can see here, this is data. These are 3 nucleon absorption. This is the momentum of the sigma. So we could measure it, but obviously the phenomenological calculations which we do of the nuclear absorption are too crude. So we really need, please help on us, the amplitude of these processes in terms of momentum in the momentum space. Thank you.
Very interesting, really. Are there comments or questions? Angus?
Hi, Christian. Thank you for all this overview. I have essentially a technical question. Do you have, because I mean, what you can obtain by analyzing this data from Chloe is really interesting. Do you have access to all the data? So is there a chance that you get more data to analyze, or you have all the data that right now that you can have?
We have ongoing an agreement with Chloe, which more or less ends with these 2 last measurements, the lambda triton and the sigma 0 pi 0 measurement. But we are confident that since Chloe was also honestly suggested to look into all the possible channels that they have in their really amazing experimental data sets. So we hope that ended these 2 papers, we will go with a new agreement with them, and we will have the possibility. The new Chloe data also, it's extremely interesting. They have a comprehension and the Monte Carlo of the detector, which is obviously more refined. That this is 2004-5 data, which I showed you, but we have the Chloe 2 data, which is now ready there. They have new detectors, inner detectors, so the vertices can be even better recognized. So yeah, I'm very confident that we will have a new agreement for the future, and we can go on with this.
Thank you.
For these, obviously, for this measurement here, some dedicated target would be needed, some inner helium target.
Thank you.
Are there other comments? If not, we thank the speaker again. And we move to the 4th presentation of this first session. Yaroslava Obertova, I hope I pronounced correctly your name. She will talk about K- nuclear interaction, K- nucleus quasi-bound states, and K- atoms.
Yeah.
Sorry.
Thank you. Good morning, everybody. So the meson-baryon and baryon-baryon interactions are currently described by so-called chiral coupled channel interaction models. And these chiral models were also successfully applied to the description of K-minus neutron interaction. And the parameters of the models are fitted to the K-minus proton scattering data, threshold branching ratios, as well as energy shift and weight in kaonic hydrogen. So there exist several of these chiral models describing K-minus nucleon interaction. And here in this plot you can see the real and imaginary part of the free space K-minus proton scattering amplitude in these state-of-the-art chiral models. And as you can see, all models agree with each other at and above threshold, since their parameters are fitted to the data in this region. But below threshold, all the models have very different behavior. In the next figure, there is the same picture, but for the free space K-minus neutron amplitude in the state-of-the-art models. But you can see that in this case, the situation is different, and there is no good agreement of all models, even at and above threshold. A very important source of information about K-minus nuclear interactions are kaonic atoms. And their analysis gives us unique information about the K-minus nuclear potential. And a sensitive test of any K-baryon interaction model is its ability to fit the broad database of kaonic atoms. But when you do that, when you construct the kaonic atom nuclear potentials from chiral K-n single nucleon amplitudes, then you are in generally unable to fit the kaonic atom data. You can see the chi-square 65 for all the chiral models I showed you. And why is this so? Why is this happening? And the answer is simple. The chiral models do not include the K- absorption on 2 and more nucleons. And this multinucleon absorption is very important for a realistic description of K- nuclear interaction. In the analysis of kaonic atoms done by Friedman and Gall, they added this phenomenological multinucleon potential to the K- single nucleon optical potential constructed from the amplitudes from the chiral models. And the form of the phenomenological potential is here. And they fitted the parameters of this multinucleon potential for each of the chiral models separately. So, and when they have done this, then the description of the kaonic atoms increased significantly. The chi-square 65 goes down to 101 or up to 125 for all the models. And you have equally good fit for all of them. Okay. And you can further distinguish between the various K-baryon interaction model by testing their ability to reproduce experimentally deduced fractions of a K- single nucleon absorption from bubble chamber experiments. And when you do this, then you find out that only 3 of the models, namely Prague, Kyoto, Munich, and Barcelona models, are able simultaneously describe kaonic atom when supplemented by this multinucleon, phenomenological multinucleon potential. They are able to simultaneously describe the kaonic atom data and the K- and single nucleon absorption fractions. And another confirmation of the validity of these 3 models was also done by recent measurement of the K minus n 2 pi lambda scattering amplitude by Amadeus collaboration. And the 3 of the main models are compatible also with this measurement. So having all this information about the K minus nuclear interaction, we explored the possibility of K minus quasi-bound states in many-body systems in nuclear starting from carbon up to lead. And first we did constructed proper in medium K minus amplitudes from the free space chiral amplitudes, taking into account the Pauli correlation in the medium. And then we constructed the energy-dependent K minus optical potential comprising of the K minus single nucleon potential based on this K minus n chiral amplitudes plus this phenomenological multinucleon potential. And with this, we solved the Klein-Gordon equation and we calculated binding energies and weights of K minus states in nuclei. And the nucleus was described by, within the relativistic mean field model in our calculations. But when you insert K minus inside a nucleus, you probe the potential around saturation densities. However, experiments with kaonic atoms can probe reliably the K minus optical potential only up to about 50% of saturation density. And beyond this limit, the shape or the form of the phenomenological multinucleon potential is just a mere extrapolation or continuation of the analytical formula. So in our calculations, we considered 2 limiting cases for this multinucleon potential. First, in this which we call full density option, we took the phenomenological multinucleon potential as is in the entire nucleus. And then, in the second option, which we call half density limit, HD, we fixed the value of the K minus multinucleon potential at constant value at 50% of the saturation density for densities larger than 50% of the saturation density. And using these 2 versions, we did the calculations. And here in this table, I present the results of 1s K minus binding energies and corresponding weights in various nuclei calculated using these 2 options for the multinucleon potential in Kyoto Munich model and Prague model. And for comparison, you can see here also binding energies and weights calculated using only the underlying K minus and single nucleon potential. So you can see that when the multinucleon absorption is taken into account, the weights increase considerably, while the binding energies change only slightly. And for the full density option of the multinucleon potential, the anti-kaon is even not bound in most of the nuclei because the multinucleon absorption is so strong. Okay, so we know that the K minus multinucleon absorption is very important, and it actually is about the K minus multinucleon absorption fraction in the surface region of the atomic nuclei represents about 20% of all absorption, of all K minus absorption. And so far, it was mainly described by this phenomenological multinucleon potential, as I showed you. So it would be good to have also some more microscopic description of this multinucleon absorption, and which would be connected somehow to this chiral K minus n models, interaction models. And the first approach in this direction was done by Sekihara et al., who developed the first microscopic K minus nn model for K minus nn absorption in nuclear matter using free space chiral amplitudes. And in the model, he evaluated the imaginary part of the K minus NN potential. And we went even further, and recently we have developed a model for the K minus 2 nucleon absorption in symmetric nuclear matter. And in the model, the K minus 2n absorption is based on a meson exchange picture. In the model, we employ the K minus n chiral amplitudes from Prague and Barcelona models. We took into account the Pauli correlations in the medium for the K minus n amplitude. And moreover, we also derived the real part of the K minus NN optical potential. And within this same approach, we derived also the K minus single nucleon optical potential. So in this way, we obtained K minus single nucleon, K minus 2 nucleon, total K minus optical potential within one approach and one chiral model. And so in the model, we can describe the K minus single nucleon absorption by this Feynman diagram, where the dashed lines denote mesons, solid lines baryons, and the dashed shaded circles denote the K minus and T matrices derived from a chiral model. The 2 nucleon absorption is described as a meson exchange process, and the Feynman diagrams describing this 2 nucleon absorption of K minus with 2 nucleons at rest is depicted in these figures. And we took into account also the so-called exchange Feynman diagrams for the 2 nucleon absorption, which result from the antisymmetrizing the initial N1, N2 pair, and also from the exchange of the final state nucleon and hyperon. And we calculated or we evaluated the K minus n and K minus nn potential as a sum of contributions coming from all possible absorption channels. In case of the single nucleon absorption, we have 7 possible absorption channels. In case of 2 nucleon absorption, we also have 7 possible channels, but each of the channel can proceed via several direct and exchange diagrams, depending on the possible meson exchanged. So the total potential is just the sum of all contributions in each channel. Okay, so having this model, we wanted to test it against some experimental values, and we calculated the ratio for lambda proton, sigma 0 proton pair production, which was recently measured by Amadeus collaboration. So here in these figures, you can see the experimental value from Amadeus is this gray box, including error bar, and then our calculated ratios in the Barcelona and Prague model. And first, we evaluated the ratio using only free space amplitudes. And you can see that the ratio is out of the experimental value. And when we took into account the Pauli correlations in the amplitudes, then we have a nice agreement with the experimental value. And this also nicely illustrates the importance of in-medium modification of the free space amplitudes. Okay, so next we wanted to test our K minus NN model even further, and we applied it in the calculations of kaonic atoms. We used Barcelona model amplitudes, again take into account the Pauli correlations in the medium, and we calculated microscopic K minus N plus K minus NN potentials for 23 nuclear targets and confronted them with the kaonic atom data. Next, we also supplemented this microscopic potential by an additional phenomenological term which should address the 3 and 4 nucleon processes. And here there are results of this this comparison with the data. So here in this table, you can see the values of chi-square 65 resulting from comparison of predictions with kaonic atoms using K- single nucleon and then K-n plus K-nn microscopic potentials. So you can see now that when you include the two nucleon absorptions, the description of the data significantly improves. But yet, you still have to add some phenomenological term in order to decrease the value of chi-square 65. And when you do that, then you result with the fit which is as good as the best fit K-n plus phenomenological multinucleon potential based on Barcelona amplitudes. And in the analysis, we fit the parameters of this additional phenomenological term. And here you can see the results for this complex amplitude B and the parameter alpha. And one thing worth mentioning is that in this case of Pauli amplitudes, I did not mention these are just two methods of accounting the Pauli correlations in the medium. One is directly include the Pauli modifications in the chiral models, and the second one is modifications of free space amplitudes by the so-called WRW method based on multiple scattering approach. So in this first case, we obtained a negative value for the imaginary amplitude B, which means negative absorption. And that's not really physical. And it actually tells us that the original K-n plus K-nn microscopic potential in this case seems to be too absorptive to allow some additional multinucleon absorptions. And I want to also discuss this parameter alpha of this phenomenological potential. This parameter controls the density dependence of this extra phenomenological term. And when you intend to describe 3 or 4 nucleon processes, you expect to have alpha equal or higher than 2. But our fit yielded values for both cases less than 2. And this tells us, again, that there are some deficiencies in these microscopic K-n plus K-nn potentials. Possible solution to this problem could be proper insertion of hadron self-energies in the K-nn model as well as into the K-n chiral amplitudes, which is not done in the current version of this model. And the last result I want to show is that we calculated branching ratios for primary interaction production in kaonic carbon atom using our K-n plus K-nn microscopic potentials. And here you can see where mesonic branching ratios, non-mesonic branching ratios in both models, Barcelona and Prague. And the experimental data on primary interaction branching ratios from bubble chamber experiments are shown here for comparison. So you can see that our model yields reasonable agreement of the branching ratios with the experimental data. Both models yield equally or very similar results for the branching ratios. And the total two-nucleon absorption ratio is consistent with the latest two-nucleon absorption ratio measured by Amadeus collaboration. Okay, so this brings to my summary. So the K-n interaction is nicely described by chiral meson-baryon interaction models. However, they lack or they do not include the K- multinucleon absorptions or interactions, which are very important for realistic description of K- nucleon interaction. And the inclusion or the comparison of predictions for potentials based on these chiral models with the kaonic atom data yielded constraint on the meson baryon models, and actually only 3 of them are able to reproduce the data. And then, with this knowledge of multinucleon absorption, we calculated K-minus nuclear quasi-bound states in various nuclei. However, our result shows that if K-minus quasi-nuclear bound states in many muddy systems exist, they have huge widths, considerably exceeding their binding energies. And then we have developed a microscopic model for this K-minus 2 nucleon absorption. And we confronted the microscopic K-minus n plus K-minus n potentials with kaonic atom data. And our results show that the description of kaonic atom data improves considerably when you include this 2 nucleon absorption. However, you still need some additional multinucleon term to get to decrease chi-square value to be less than 2. And again, in the model, we only include the Pauli correlations. And now we would like to further improve the model by including the hadron self-energies properly. So stay tuned, new results will come. Thank you.
Thank you very much. This has been a very interesting and comprehensive presentation. Are there questions or comment? Yes, Otto?
Thank you very much for the talk. Can you go to slide number 22?
22?
Yeah, in this comparison, the calculations are done in carbon, right? Mm-hmm. Because you are comparing with helium and carbon. Because apart from this data that you have here from Bubble Chamber and from Amadeus, there is also the FINUDA data that is very detailed in the sigma plus and sigma minus channels, both 1 nucleon absorption and 2 nucleon absorption. And from helium to carbon, they scan from 6 lithium to oxygen, and there is a change. So it's not constant as, for instance, we saw this band from, in one of your slides from Gal taking bubble chamber experiments. So maybe you can also take a look at this FINUDA data that is very, very detailed in the sigma channels.
Okay, thank you. So we'll take a look on it.
Are there questions, Walter?
Thank you. I just want to comment that these calculations are interesting because they are very sensitive to the K-bar n amplitude below threshold in which there is the effect of the lambda 1405 resonance. So this is why different models and different treatment of the many-body amplitude can give you substantially different results. So I'm really looking forward to see what the result will be when you include the self-energies of the kaons, because if at the level of the Pauli, when you include the two-body absorption with the Barcelona amplitudes which have been modified, medium modified by the Pauli effects, you need extra negative absorption. This is not good. This apparently doesn't look nice, but I think that with the medium modified amplitudes that contain the self-energy, you will get much less nucleon absorption, and maybe already at this level you could obtain a good agreement with the kaonic atom data. I just wanted to make this comment.
Yes,
Thank
you're
you.
right.
Thank you. I don't see any hands, so
There's
I
one,
think.
Christian.
Oops. Oh, too far. Sorry.
Thank you, don't worry. No, just very briefly, I wanted to comment also on Angel's comment and on your very amazing work. Please also, you suggest us, Angel asked, what will be the future of the collaboration with Chloe, and the data which was collected recently. So if you have new ideas, experimental input which you would need to even constrain better your calculations, suggest us, and let's go in a common direction on that. Okay?
Okay, we keep in touch then.
So I think that now we can thank the speaker again, but also to thank all the speakers of this session. So we close the session, and I think we can go to the coffee break. Okay.
Okay, great. Good morning, everyone. So this come to the last session of HYPE 2022. I hope so far everyone enjoy it and you enjoy the last one. The first speaker for the last session is from Carnegie Mellon, talk about decay of the lambda 1405, sigma 0 pi 0 by Nalanga. Welcome. So you can start your presentation.
Can you see my slides?
Yes, we can hear you and see your slide clearly.
Okay, great. Yeah, so I'm Nilanga Vikramarajchi, a postdoc at the Catholic University of America. And first of all, I would like to thank the organizers for giving me this opportunity to present at this conference. So I'll be presenting on the decay of the lambda 1405 to sigma 0 pi 0 measured at GluX. So first, an introduction. So the lambda 1405 is located just below the k-baryon threshold, and its resonance with the spin half and negative parity. And in the quark model, lambda 1405 can be considered as a spin orbit partner of lambda 1520. So the interesting thing about this lambda 1405 is, as you already heard from previous presentations, that the invariant mass or the line shape of lambda 1405 is seen from the experiments to be distorted from a Brevigner form. And the lambda 1405 decays 100% into sigma pi, but it assumed to couple strongly to the k-baryon channel. And some chiral unitary models suggest the lambda 1405 to be composed of two isospin 0 poles. In fact, recently PDG has added the lambda 1380 as a 2-star resonance. You can see in this table. So the lambda 1405 to sigma 0 pi 0 decay mode is very important because it's pure isospin 0. That means unlike the charge decay mode sigma plus pi minus, sigma minus pi plus, where there's contamination from sigma 0 1385, the sigma 0 pi 0 has no contamination, and the data is very limited for this sigma 0 pi 0 mode. So in these equations, you can see the differential cross section d sigma dm for the three modes, sigma pi modes, written in terms of the isospin contributions. So, and we can see that pi 0 sigma 0 mode has only the isospin 0 contribution. So this means this sigma 0 pi 0 decay is very useful to study the lambda 1405 line shape. And the GluX experiment can reconstruct neutral showers well. So it's ideal to reconstruct the sigma 0 pi 0 decay mode. And studying the lambda 1405 line shape would provide more information on how the sigma pi and NK bar channels contribute to its production. So now I'll show a few previous measurements for lambda 1405 to sigma 0 pi 0. So there's an early observation in bubble chamber experiments in 1961. This was K minus proton interactions at 1.15 GeV/c. But what I want to focus was these recent experiments. So on the left side figure, you can see this measurement by ANKEC. So they did proton-proton going to proton K plus Y0. So Y0 means hyperon. And they used 3.65 GeV/c momentum proton beam at Corsi-Jülich and looked at the Missy mass of proton K plus, and they extracted the lambda 1405 events. And then they got the total cross-section for the proton K plus lambda 1405 to be 4.5 microbarn. But here the statistics was limited in this measurement. So this right side figure shows the photo production measurement done by the class at Jefferson Lab. So they did gamma p to K plus sigma pi, and they had high statistics for all the three sigma pi modes. And in the figure, what it's shown is the d sigma dm for the sigma 0 pi 0 mode. And they did this in the center of mass energy from 1.95 to 2.85 GeV, and they fit the d sigma dm distributions to extract the lambda 1405 line shape. So both of these measurements, when they extract the sigma 0 pi 0, they use missing mass technique. So now to a more recent measurement. So this is done by VGOD at ELSA. So they reconstruct the exclusive reaction gamma p to K plus pi minus proton and 3 photon final state. So an issue with this multi-photon final state is that it leads to large background under the sigma 0 peak. And also the statistics are also limited in these exclusive measurements. So you can see this VGOD measurement of the sigma 0 pi 0 invariant mass, and they estimated the background contributions from simulations, and then subtracted the background, and then compared this d sigma dm, this normalized measurement to the NK and class data points. So, and also they compared with the theory model prediction. So the GlueX can exclusively reconstruct this state with the use of kinematic fitting to reduce background and optimize mass resolution. So I'll briefly mention about the GlueX experiment. So the GlueX is located in Hall D at Jefferson Lab, USA, and this is a photo production experiment. Main goals of the experiment are to search for hybrid mesons, study light quark meson spectrum, and the hyperon spectroscopy. So now about the GlueX spectrometer. So I'll just briefly mention, you will hear more information from Peter Pauli in the next talk. So we have a liquid hydrogen target for the proto production, and so we have electron beam hitting a diamond radiator, and then the Bremsstrahlung photons are tagged in the energy range 3 to 11.6 GeV, and also we have linearly polarized tagged photons around 9 GeV produced by coherent Bremsstrahlung, and so we have nearly 4 pi angular coverage, and we detect the charge tracks using drift chambers and photons using calorimeters, leading to exclusively reconstruct the final state of the reaction. So now moving to my analysis. So for the UN selection, so I'm using GlueX experiment phase 1 data. So also these events only selected in the photon beam energy range 6.5 to 11.6 GeV. This corresponds to a luminosity around 423 inverse picobarns. And in the left side, you can see this diagram for the decay chain. So gamma proton going to K plus lambda 1405, and lambda 1405 decays to pi 0, sigma 0, pi 0 decays to 2 photons, sigma 0 to lambda and a photon, and lambda to pi minus proton. So we applied kinematic fit, conserving for momentum and constraining the event vertex. And also the pi 0 and sigma 0 masses were constrained in the kinematic fit to improve sigma 0 pi 0 mass resolution. And on the right side, you see the Mandelstam T distribution. So this Mandelstam T was calculated using the beam for momentum and the K plus for momentum. So we have a lot of events in the low T region for T channel production, and there's also U channel contribution. But for this analysis, we focus on the T channel production of lambda 1405. So now for the invariant mass of sigma 0 pi 0, so I looked at the minus T minimum 0 to 1.5 GeV squared region and plot the sigma 0 pi 0 invariant mass. And we can see clear peaks of lambda 1405 and lambda 1520. And we have around 13,350 counts in the lambda 1405 region. This is assuming there's no background. So we also see a sharp drop of yield for the lambda 1405 at K-bind threshold. So this is suggesting that our resolution is sensitive to these threshold effects. And also the simulations indicate that we have a good resolution. So this is a sigma 0 pi 0 mass resolution for sigma 0 pi 0 generated mass. And in the lambda 1405 region, we have good resolution. So now for the lambda 1405 line shape measurement. So this is the d sigma dm, sigma 0 pi 0. So we have to still finalize the normalization. So the numerical values are not shown on the y-axis. The uncertainties are only statistical, but we can see that clearly the lambda 1405 line shape deviates from a Breivik form. So we tested two hypotheses for fitting the lambda 1405 line shape. So on the left side, we fit a single lambda 1405 curve. So this is the red dashed curve. So this parameterized with one plateau amplitude, and we have a incoherent lambda 1520 shown by the blue curve, and there's background, incoherent background as green curve. And this fit gives a chi-squared of degrees of freedom around 5.1, and the centroid is located at 1407 MeV for the lambda 1405 state. And on the right side is a compound coherent lambda 1405. So there are two states, two flat amplitudes. So there are no strong phase between them, and a common flat factor for the two amplitudes, and these are shown in the red dashed curves. And the coherent sum of these two are shown in the red dotted curve. And similar to the left side figure, there's also lambda 1520 and background incoherent amplitudes. So this fit gives a better chi-squared of degree of freedom, around 3.5. So this is better fit compared to the left side. And the lambda 1405 split into two centroids. So we have around 1387 MeV and 1409 MeV. So we then looked at d sigma dm for three different minus T minimum bins from 0 to 0.35, 0.35 to 0.6, and 0.6 to 1.5 GeV squared. So in this d sigma dm distributions, we see that there's a T dependence in the lambda 1405 line shape. So then we applied the lambda 1405 two state, the fit I showed earlier, to all of these three different T-bins. So the incoherent lambda 1520 and background, they are the same kind of fit. So what we see is that in these T-bins, the relative intensities of the two lambda 1405s, they change with the minus T prime, and So the fits describe well the data well in all the minus T prime bins. So to summarize, the GlueX is ideally suited for exclusive reconstruction of lambda 4.5 to sigma 0 pi 0. We have the highest statistics obtained so far. So we have around 5 MeV resolution in sigma 0 pi 0 mass near the lambda 1405. And lambda 1405 land shape clearly seems to deviate from a Breivik form. And the fits to line shape favor a composite or two coherent states picture for the lambda 1405. And we also observe T dependence for the lambda 1405 line shape. And GlueX preliminary results supports previous theory and experiment suggesting the lambda 1405 is a composite baryon state. Thank you.
Thank you to the speakers. Any questions and comments from audience?
Thank you. Nice talk. The question, please, with the fitting where you had the coherent sum of the two peaks. Was the mass and the width constrained by your data, or was this from theory before? So these, I think you had one of the T dependence as well. The next slide.
Yeah, so for each of the fit, so there are fit parameters, the mass and width. But we didn't code the values here, but they are not fixed. So there are free parameters in the fit.
Okay, thanks.
Any other questions? No? Okay. Let's move on. Thank you. Thank you for the speakers.
Thank you.
Nice result from GlueX. So
Thank
next
you.
speaker will talk about another subject from GlueX, right? All right. This is a strangeness program at GlueX.
Yes, thank you. First of all, thanks to the organizers for giving me the opportunity to present the GlueX Strangeness program on behalf of the GlueX collaboration. When selecting the results I'm going to show, I focus mainly on baryons. We also have some meson results, which I might be able to just briefly discuss at the very end, but most of the stuff I'm going to show is about hyperons at GlueX. It's quite nice that Nilanga gave an introduction to where we are, but still I want to show you that GlueX basically sits here. We are like located at Jefferson Lab in Virginia. You have this bird's eye view here of the CBAF accelerator complex with the 3 experimental holes, and I think we have seen results from all holes during this conference, but GlueX sits in this new extension here, which was built when the CBAF accelerator was upgraded from 6 to 12 GeV a few years ago. GlueX is quite different from the other experiments we run at JLab in that we don't use the electron beam directly. At GlueX, we want a photon beam to do photo production experiments. And the way we go about this is that we basically use CBAF's electron beam that comes in here, and we scatter it on a very thin diamond radiator to produce coherent Bremsstrahlung radiation. The electrons that scattered on this radiator lose some energy, so we have a magnet, so we can bend them away and measure their energy very precisely, basically by measuring where they actually hit a focal plane detector that's sitting here. So we know for each individual photon that we produce the energy very precisely. Then our photons travel for 75 meters, so this is not to scale. They travel for 75 meters and then they're collimated by like a 5 millimeter small hole to make sure that we have a very nice photon beam hitting our liquid hydrogen target that's sitting in the center of the detector setup. And well, surrounding this target are several detectors that are not unlike other particle physics experiments. So you have some drift chambers forward and central to do identification tracking of charged particles. Everything sitting in a magnet means we can measure their momentum fairly accurately. And then we have calorimetry surrounding the drift chambers and in forward direction, and we also have a time-of-flight detector sitting here to help us with PID. I mentioned that we have this photon beam, and you can see the photon beam spectrum shown here on the top. It's plotted on the x-axis is the photon beam energy, and shown on the top half in plot A is the photon flux. And you see we have, because we use coherent Bremsstrahlung radiation, we have the strong enhancement, which is at about 9 GeV, and that's why you sometimes hear about GluX as a 9 GeV photon beam experiment. And if you produce coherent Bremsstrahlung radiation on a diamond and you orientate the diamond just right, you can get linearly polarized photons, and the linear polarization peaks exactly where this coherent peak is, and we have about 40% polarization in GluX. So, as I mentioned, we have fairly good resolutions for charged and neutral particles, and we also have almost 4 pi acceptance due to the large boost. So if you have like 9 GeV photons coming in, everything is boosted fairly forward. So this acceptance in the lab frame translates to basically 4 pi acceptance in the center of mass system. I also quickly want to mention that since 2019, we have an additional detector which sits right in between here, which is a so-called DIRC detector, detection of internal reflective Cherenkov light, which greatly improves our pi and k separation and means that we can push our GluX strangeness program much further in the future. But the results I present today are about the GluX, come from the GluX1 dataset. So the first result I want to show is our lambda anti-lambda analysis. That there are many interesting reasons to look at this. One, for example, is that BEST3 saw an interesting threshold enhancement. When you look at lambda anti-lambda in GluX, reconstructed in this final state where the lambda decays to proton pi minus. And the first thing we can do is we can study the production mechanisms, but we can also do cross-section measurements. You see here the 2D invariant mass plot where you see the proton pi minus versus pi plus antiproton. This very nice enhancement here. We basically have a lambda bar. And in GluX1, we have about 400,000 of these events to study. So, as I said, the first thing we want to do is we want to understand how they are actually produced, and what you can do fairly easily is you can just boost into your center of mass system and look at the cosine theta distributions of your 3 particles. And if you do this, you notice straight away that they don't look the same at all. So the lambda and the anti-lambda have very different distributions, and the proton as well. And then you can, in a very hand-wavy way, think about why this spectrum could come about, and then you might realize that you have various different ways you can actually produce this lambda bar reaction. And if you have, for example, a reaction like here, where you have the lambda bar produced at the top vertex from your photon recoiling against the proton, you would expect to see them going forward in the center of mass system. While if you have a production mechanism like that, you would expect the lambda bar to go forward, but the lambda should go backwards, and this is also supported by our data. This intermediate region, which seems to be very populated by the lambda bar, but not the other two, this could probably come about fairly easily if you imagine that you have these double Reg exchanges, where it's not just one particle that's exchanged here, but you actually have like an intermediate step. So yeah, this is a very hand-wavy way of looking at things, but it's quite nice to think about these reactions in those diagrams. As I mentioned, we also then go on to measure cross-sections, so I show you some preliminary results. Here for the invariant mass, the cross-section, d sigma dm, basically for the lambda bar system, and for the proton lambda bar system. Gray is what you would expect if everything was just purely phase-space and goes in all directions the same way. And you see that this is actually not what we see in GluX at all. We have a very different shape, and of course the first association you might have is, well, maybe this is one of those threshold enhancements that you see, but actually you could also you get very similar shapes just by the production mechanisms I've just shown earlier, because our production mechanisms are not isotropically in all directions. So this is an investigation. We need to figure out how we can basically remove this production process influence on this shape to really understand if there's a real threshold enhancement going on here. We can also measure the lambda bar differential cross-section differential in momentum transfer T. And there are some theory predictions, and as you can see, our data doesn't quite match with that. So, of course, this is due to the fact that there isn't really any data yet those theorists could work with when they built their models. So they're sort of stepping in the dark, but we hope that we can help with improving those models. Also, what's going on right now, I don't have a slide to show, but we're also working on measuring the lambda polarization. This is something Nilanga just talked about, so I actually don't need to spend much time on that. Just to say again that this is a very interesting analysis that's currently performed at GLUEX. And just to flash those money plots again, basically we see that we have this apparent T-dependence in the line shape, and our line shape seems to support the two-pole structure. And if you do like very simple fits where you just use two coherent flat A amplitudes, you can reproduce the, you can get a line shape that fits the data quite nicely, but you really need those two amplitudes in there. The next thing I want to talk about is the next excited state in the lambda excited lambda sector, which is the lambda 1520. And what we did here is, again, we wanted to study the production process, which is something quite important for us in our initial GLUEX data analysis. So what we look at is the reaction gamma proton going to K plus, K minus proton, and then you look at the environment mass spectrum of the K minus, basically going from thresholds all the way up to like 2.4 GeV. You see many interesting peaks and bumps and structures, but the one we are interested in for this analysis is this very narrow, fairly isolated peak, the lambda 1520. And what we do in order to learn about the production mechanism is we basically boost into the Gottfried-Jackson frame, which is shown here. So it's the lambda 1520 rest frame, where you align your z-axis accordingly. And then we measure spin density matrix elements, which are basically a parameterization of the angular decay distribution. So you measure this K minus in this Gottfried-Jackson frame, and then you can do a fit to the data and extract 9 independent spin density matrix elements called rho. And there are 2 model calculations kindly provided to us by Yoon Kong, and as you can see, our data is in some tension with their model calculations, but again, I want to stress that this is the first data that's actually available in this energy region. So again, they had to like guess a bit about quite a few things, but again, our data can hopefully constrain the model going forward. In terms of interpreting those spin density matrix elements, I always find it quite hard to just look at numbers and know what they mean. So one nice way to think about them is if you look at actually combinations of spin density matrix elements. So what you can do is you can go back to this diagram here, this production diagram, where you exchange a particle X, and then you can think about this particle X as some, the fact that it has some what we call naturality. So you basically take the parity and the spin of this particle, and you can define this quantity, which is called the naturality. And a natural particle would be something that's a vector or a tensor meson, while unnatural particles are pseudoscalars or axial vectors, for example. And what you find when you do a bit of maths is that you can form combinations of SDMEs that contain only natural amplitudes or only unnatural amplitudes. So you can recast your SDME results in those combinations, and then what you see is that basically on the top row here you see the natural combinations, and on the bottom row the unnatural combinations, and you see that this exchange really seems to be dominated strongly by the natural exchange amplitudes. But again, there's more work needed in order to tune the models correctly to the data. Of course, a very important ingredient if you want to understand the production process properly is you need to know about cross-sections. So we also, in the in the process of measuring differential cross-sections, those SDMEs have been published, I should have pointed out maybe, while those cross-sections are now just preliminary results. So we measure differential cross-sections in 7 bins of photon beam energy, and then you can, of course, also integrate those differential cross-sections to get something like a total cross-section, which we can compare to previous data. So SLAC in the 70s measured the data point here, and then CLASS in, I think, 2013, they measured some data as well. And we see like the GluX energy range, we sit somewhere in between them, and we seem to be quite nicely on the right trajectory here. We do have actually also a bit of data on tape in this energy region, so hopefully we can fill this gap soon and provide some data up to about 5.5, 6 GeV. The next reaction I want to discuss is the sigma zero production that was also published. So what was done here is we measured something called the beam asymmetry sigma, not to be confused with the baryon sigma. So the idea here is that basically you use your linear polarization and you measure this reaction for a linearly polarized beam that's orientated 0 degrees to the lab or 90 degrees to the lab. And then you could do the same with minus 45 and 45. So basically you build up those combinations, and what you then just have to measure is the yields corrected for the different flux and the different orientations. And if you do this, you get a very nice asymmetry, this yield asymmetry, which you can fit with a cos2phi function to extract this parameter sigma. And if you do this, you find that sigma is sitting at pretty much bang on 1, which, if you compare this to some model calculations, suggests that also this this production proceeds via natural exchanges. Also, I want to point out that in this reaction, although I don't have the plot here, we see a very sizable U-channel contribution as well. So this reaction also seems to be produced quite a lot in U-channel, which is a reaction where the sigma is actually produced here on the top vertex, and you exchange a virtual baryon, which recoils against the proton to produce the K+. I'm not sure how many people of you attended Chandra's talk yesterday in the parallel session, but we are also able to measure some cascades at GluX. The situation with the cascades is quite unsatisfying in that we would expect to see quite a lot of cascades, basically as many as we expect to see n stars and deltas. But if you open the PDG, there are only really like 6 well-known states, and by well-known I mean a rating of 3 stars or better. And the idea is maybe we can provide some valuable data on photo production. Of course, photo production experiments not many have been performed to look for cascades, because you need to produce strangeness -2, basically out of nothing. So you can easily do this with a high cross-section photo production. But we can see what we find, because GluX is quite good at measuring charge in neutral final states, right? So maybe we can help here. So this is what Chandra presented yesterday in one of the parallel sessions. And basically, as I said, you need to produce strangeness -2 from scratch. So the only way to really do this is if you go through an intermediate resonance, some Y star, which you don't really know, which might be very heavy, very broad, which then decays into a cascade and a K+. And then you can look for the cascade decay, for example, into K minus lambda. And if you look at the K minus lambda in Berry mass, you see a very nice peak sitting at exactly where you would expect the cascade 1820, which is a 3-star resonance. As far as I know, I think it's the first time that this resonance was measured in photo production, and we can measure the cross-section of that. Well, we can measure the cross-section times the branching ratio, because the branching ratio into K minus lambda is not known. But yeah, nevertheless, we can do that. What's quite interesting when you look at this spectrum is that actually you would expect many other cascades also to show up in this K minus lambda final state, but we don't see that. So we only really see this 1820. And yeah, of course, the question is, why is that? And so far, we don't know. It might be related to the production process, of course, that maybe whatever intermediate Y star we have to produce here doesn't like to decay into the others or whatever. It's something we're looking into right now. We also see many other cascade states in GlueX. Basically, you always have the similar reaction in the first place. You produce some Y star, and then you look for different decays. And then, for example, if you look at the lambda pi minus, you see the very nice strong peak of the cascade ground state, the charge cascade. In pi 0 lambda, we see a very nice signal for the neutral cascade ground state. And we also have some data on the higher mass Xi minus 1530 in decaying into pi 0 cascade minus. So we see quite a lot of the known cascade states, not all we expect, but quite a few. And we are currently in the process to measure differential cross-sections and total cross-sections for those reactions. So I said I only focus on the baryons, the hyperons, but I think I might have 1 minute to quickly discuss that we're also having a strangeness program in the meson sector. So we see actually quite a few different K-stars in many of our final states, often showing up as background when you actually look for the hyperons, which is quite interesting. But we also have a few people looking for Strangeonia, so SS bar states. There's this known 1680, and we have people also looking for this Y2175, which was seen by various experiments, for example, Babar decaying to phi eta, which is one of those states that could potentially be Strangeonia or something more like a tetraquark or maybe something completely different, we don't know yet. I mentioned that we are now taking data with an improved detector, improved for pion Kane separation, and this is our GlueX2 data set, and then we really hope to push this program much further because, of course, for all these reactions, you need good K pion separation power in forward direction. Good. Let me summarize. I think GlueX has an exciting strangeness program, and we make very good progress in many different analyses. As I mentioned, now we have this new DIRC detector sitting here, and GlueX2, including this new DIRC, will improve our data for final states containing strangeness dramatically, and this will really help us to perform photo production measurements with so far unprecedented statistics, especially at those very high energies. If you have interesting ideas for what we should look for, what we should measure, please let us know. We are really open for suggestions. We have a huge data set, not enough manpower to look at all those things at the same time. So if you have ideas to help us prioritize what we should look for first, we're really happy to hear that. And of course, you can't do any experiment without a lot of money, so we also like to thank our funding agencies and the computing facilities helping us to actually crunch the data. Thank you.
Thank you so much for this nice review of JLab GlueX program, strangeness program. So it's very nice. Any questions, comments, suggestions?
Hi, nice talk. I would like to, I was intrigued by this plot that you showed on the lambda anti-lambda invariant mass pair. What is the energy at the, okay, so this is the just.
Somewhere here? Or?
Yeah, okay. So could it be a kind of a meson that decays into lambda anti-lambda?
Right, I mean, this is partly how you could produce this. If I go back to this, what I draw here as a blob, of course, this could potentially be some meson that is produced, which then decays into lambda lambda bar. But as I said, we don't know yet for sure. We can't, like current state, we can measure this cross-section and get the numerical values, but to interpret this properly, we need to make sure that we also take this production process properly into account and have to then see if this enhancement that we see is actually a state or just kinematics that push everything into this part of phase space.
Okay, thank you.
Okay, any other? No? Okay, let's thank our speakers. So let's move on to the next speaker. Okay. Professor Gogami talk about strangeness physics at J-Park. Go ahead.
Thank you, Chairman. First of all, I'd like to thank the organizers for giving me a chance to talk about our research activity at J-Park. I'm Gogami from Kyoto University. So today, I'll talk about the strangeness physics programs at J-Park. So we are now installing a new spectrometer systems in the K1.8 beamline. So, all right. Then, so this shows that K1.8 beamline, schematic of the K1.8 beamline. So we have the production target here, and we hit the proton beam onto the T1 target to produce a lot of kaons. And then these kaons is transported to our experimental hall by by this beamline. And in this beamline, so we have the two stages of electrostatic separators combined with the mass slits. And thanks to them, so we have very high intensity and high purity kaons in this experimental hall here. And at the end of our beamline, so we are now installing our new spectrometer systems, a so-called S2S, strangeness -2 spectrometer. All right. So we have many physics programs by using our new spectrometer systems. Today, but I'm going to focus on only the strangeness physics by using S2S, particularly for the strangeness equal -2 systems here. Then, actually, we had a workshop what to do by using our spectrum systems last year. And if you have some interest, please visit this link, and you can find some files, and you can download free, and you get some ideas what we are going to do. Right? So probably some people have already heard or already noticed that there are many talks and posters which are related to these strangeness S2S systems here. So also, so you can just take a look at the files if you miss these talks. All right. So some presenters already have been mentioned about the Xi in the neutron stars. Other than the lambda particles. And here I'm showing you the MR relations, which is calculated by these TOV equations. And here, this is the example, one of the calculations by the relativistic mean field model. And you see that in this field, RMF model, they changed the Xi potential from -40 to 40 MeV. And you see that some variations here. So from this, so this is one of the example, but from this, so you can expect that the V Xi is one of the important ingredients to discuss about hyperton puzzle in the neutron stars. All right, then we are trying to investigate the Xi hypernuclear spectroscopy. So we would like to do the spectroscopy. Then, so this is calculations of the binding energy and the decay width of the cascade hypernuclei. Here, this is a system carbon-12 and Xi. This is nitrogen-14 plus Xi minus, and this aluminum-27 plus Xi minus. And here, it's several hyperton potentials, ESC16A1, B1, and HAL-QCD potentials. So you see that the binding energy, not only the binding energy, but also decay width predicted very differently, like this. So for example, you see here the 4.8 MeV for binding energy, but if you look at here, the binding energy is a little bit different, of course. And also, not only the binding energy, but also decay width is largely different, 2.8 or 0.13 in the case of this. So what we aim to do is not only the binding energy determination, but also the decay width determination. So, because we are going to do the missing mass spectroscopy, and we can observe the decay width as well. So this is a different kind of theoretical calculations. And here, this is much lighter systems, so-called, probably this is the lightest Xi hypernuclear systems. So this was calculated by the Lee-san et al. And also, these are the calculations by the Hiyama-san. But they use different interaction models here. And you see here, the Calorie EFT models. This is this binding energy for the H foci, and binding energy is for this system is 0.64 MeV. And here, if you compare, ESC model and Calorie EFT HAL-QCD models, and the binding energy is really different. And also decay weights are different. Yeah? And for these systems, the HAL-QCD, if you use the HAL-QCD potential, so bound system has not been found. So this is really interesting. Then in our experiments, so we use, as I will explain in the next slide, we are going to use K minus K plus reactions. So we change isospin by 1. So that's why if we would like to use available experimental targets, we only produce N foci. We cannot produce H foci. But of course, theory predicts that this could be bound, but this could not be bound. But I think it is very interesting to look at this system because we can do that. And also, even if this is not bound, if the decay weight is narrow enough, and in this experiment, we don't care about the bound state or not. Even if this is a resonance state, we can measure because we are going to adopt missing mass technique. So probably not now, but in the near future, we would like to look at this system as well. All right, this is schematic of our reactions. So we use K minus beam, which has the strangeness -1. And hit the target here. The strange -1, yeah. And a carbon target. And a proton in a nucleus is converted into Xi minus to produce Xi hypernuclei here. And then at the same time, K plus is emitted from the experimental target. So we measure the momenta, and the angles of K minus and K plus. This is it. Only momentum vectors of these two particles will be measured to reconstruct the mass of hypernuclei. This is it. It's really a simple experimental technique. And once you have the mass of hypernuclei here, and you can automatically calculate the binding energy by this formula. So this is really simple. And this kind of reaction spectroscopy has been already done in the past experiments. For example, at KEK, Brookhaven BNL, and in JPARC as well. And this is an example of the Brookhaven experiments. So you see that these spectrometer systems. The K minus beam is guided onto the experimental target here, and a K plus is measured by the spectrometer systems. And this is a spectrum from this experimental attempt. And you see that in the bound region, which corresponds to the negative binding energy here, because this is minus binding energy for the horizontal axis. So negative region corresponds to the bound regions. And there are some events, but no clear peak has been observed. But this is really good indications because there's something there. So what we would like to do is to determine or observe the peak structure clearly to determine the binding energy and also decay width. But they couldn't observe the peak structure, but they did some kind of analysis of looking at the core surface shape, and they've got potential informations to be about 14 MeV. This is really good information. And yes, and in the previous experiments, they've got resolutions 22 MeV at KEK, 14 MeV Brookhaven, and previous JPARC experiment 6 MeV. And in the next experiment, the JPARC, we are aiming to have 2 MeV. So this is really really good sensitivity to observe the peak structure of the cascade hypernuclei. Here, actually, already Abraham introduced in this conference. So this is another kind of analysis. It's very similar to the core surface shape analysis, but a different target. In the previous slide, I showed you the carbon-12 lambda case, but this is the case for the beryllium-9. But the same thing could be done, although this is the momentum distribution, not the binding energy distributions. But the same thing could be done. And here, you see the shape analysis by changing the potential of the cascade. And then they've got the chi-square minimum to fit this momentum distribution. And they've got the result of minus 17 MeV. plus minus 6 million, relatively rather bigger error there, but still this is really good information and it's consistent with the previous results. Okay, now, so we'll do the spectroscopy. Anyway, then we need some prediction because otherwise it's really difficult to design these experiments. And here, actually, so we use carbon-12 target. And carbon-12, as I explained, but proton is converted into the Xi. So that's why the core nucleus, so-called core nucleus, is boron 11, because proton is just missing boron 11. And boron 11 plus cascade minus. So the core nucleus is boron 11 here. This is a level structures of boron 11. And so you attach the Xi minus in the boron 11 systems. And then the level structures are expected like this. But you see here, so depending on the interaction models, level structure is very, very different because we don't have a lot of information about the interaction. So this is really chaos, but it's interesting. Then, so of course, not only the level structure, but also the production rate is also very important to analyze our experimental data. So this is the calculation by Motoba-san and Sugimoto-san. And you see here, depending on the interaction model, not only the level structure, but also production cross-section is really different. So let's see. So we are going to perform the experiment. We don't know what kind of spectrum will be observed, but we would like to observe these structures with high resolutions. Okay, so not only the Xi hypernuclei, but also double lambda hypernuclei may be observed in this reaction spectroscopy because of the coupling between cascade proton, cascade nucleon, and lambda. If this coupling is largely enough, then we may be able to observe the double lambda hypernuclei below the Xi hypernuclear region, like this. This is a prediction by Harada-san et al. Yes. Okay. Then, so this is schematic of our experimental setup. So we have two quadrupole magnets and one big dipole magnet, and we bend the particles toward this direction to do the momentum analysis. And we have the particle drift chambers for particle tracking, and then time-of-flight detectors to do the data tagging trigger and particle identification. And we need to identify kaons anyways, because we have a bunch of background particles of protons, pions. So to perform the very good, to purify the kaons in the scattered particles, so we are going to use the Elger-Cherenkov and Walter-Cherenkov counters with the refracton indices of n equal to 1.05 and 1.33. Okay, so this is a photograph of our experimental facility, experimental hall. And this was a photograph as of December 2021. This is actually end of last year, so it's simply empty. But now, it's, our equipment is squeezed together like this. We have a lot of equipment here, and actually the space is lacking, but we are trying to push our detectors in the experimental hall like this. So experiment is coming very soon. So here, this is the quadrupole magnets, Q1, Q2, and we have big dipole magnet here. And we have, now you see the drift chambers, 3 layers drift chambers in the downstreams. And after these downstream detectors, we are going to put time-of-flight detectors and Cherenkov detectors later. Probably in this month, we are going to install the frames of particle detectors here. Then so we have the very strong magnetic field, 1.5 Tesla, to bend the 1.37 GeV over C particles with the bending angles of 70 degrees. Okay, then one of the important components of our experiment is this item. So this is the active fiber target. So we are going to use the very thick target in this experiment because we would like to have the statistics for the signals. However, if we use the thick materials, so energy resolution will be deteriorated. So this is that's why we need to think about balance. But even if we use a very thick target, we would like to have a very good resolutions. So to do that, we are going to use the active fiber target. So we use these items as a target, not only as a target, but also as a detectors. And event by event, we measured energy loss, including energy struggling event by event, and then we are going to use these information, energy struggling information, to be corrected in the analysis. This was already introduced by the Harada-kun yesterday, actually. All right, then yield estimations. So this is too detailed, so I'm going to skip. But yes, we are expecting to have 100 counts of cascade hypernuclei in this experiment. This is first try. So if we think that this is not enough, we are going to propose new experiment or something. But at the first stage, we would like to have the 20 days of beam time to accumulate to have 100 counts of signals in the boundary region. And here, this is very simple simulations how the spectrum looks like. And this is a case for the 14 MeV. This is the case for the Brookhaven the resolutions, 14 MeV. But what we aim to do is to have 2 MeV, which is much better than that here. Yes. So, of course, 14 MeV is good enough to see something in the boundary region like this. But if you really want to see the peak structure, so also, of course, we need a very good resolution like this. So this is what we aim to do. And not also the carbon target, but also the lithium target will be used in the period of the next beam time, as Fujioka-san explained yesterday in the parallel session. And here, of course, this E75 experiment is to measure, the main purpose is to measure the binding energy of a double lambda hypernuclear here, H5 double lambda. So I'm going to skip the detail about this. But before measuring the H5 lambda decayed pions, so we need to know how frequently produced this hypernuclear first. Yeah? This is the first input for the decay pion spectroscopy of this double lambda hypernuclear. So that's why, as a as a phase 1 experiment of the E75 experiments, we are going to use the lithium target to produce cascade 7 lambda. So this is one of the very important the Xi hypernuclei as Hiyama-san and others predicted. All right. Then this shows the proton number and the neutron numbers. This is a nuclear chart for the S equal -2 systems. So we have a lot of very important information from the emerging experiments, Kiso, Ibuki, Kinka, Irawari events. And we are aiming to measure the beryllium-12 cascade here, and E75 we measure here. Then, of course, if we change experimental target, we can extend this nuclear chart like this. This is our goals of the future. And what I explained today is just on the missing mass technique, but also, if we equip the germanium detectors around the target, we can perform the X-ray measurements from the cascade atoms, and also maybe we may be able to do the gamma ray spectroscopy of cascade nuclear. Maybe it's difficult, but not only cascade, but also we can perform the lambda hypernuclear spectroscopy as well. So, all right. But as I said, to analyze our experimental data, we really need this theoretical support, not only the structure, but also production, because we expect that the structure, expected that the spectrum is really complicated for some cases. So please help us. And then our experiment is now planning to be done, planning to perform. Actually, the beam times will start in the beginning of 2023, maybe a little bit earlier, but this is our first aim. Pretty soon. Okay, summary. We are now installing our new spectrum systems at K1.8 beamline JPAC S2S. And then what I explained today is only the hypernuclear spectroscopy, particularly for the S equal -2 systems. And of course, we can combine not only the missing mass spectrum, but also we can do the gamma ray, X-ray spectroscopy, and decay pion spectroscopy if we equip the decayed particles detectors surrounding the experimental target. But this project will be the next attempt. And yes, then we are going to start in the beginning of 2023. Thank you very much.
Thank you for the overview for this program. And hopefully next HYPE we'll see
Yes.
a lot of data. Okay, any question, comments?
Thank you for a very nice talk. So it's very important that you are looking at the I equal to 4 psi hypernuclei. Can you, are you also planning to search for I equal to 5 psi hypernuclei? For example, hydrogen 5. Yeah.
Equal 5.
Because that system is expected to be more bound, and also we estimated the decay width is also very small.
Yeah, A equal 5. Do we have target?
Yeah.
Yeah, let's see. Yes.
That's it,
Probably it's not so easy, but yeah.
Yeah.
You said that A equal 5 is important, or to extract some information?
Because that system is more bound as compared to four-body system, and also the decay rate is small, so it's very high chance that you can see it.
Nice, yes. But probably the A equal 5 is difficult.
Yeah, I know. Yeah.
Experiment, yes. Thank you.
Any more? Okay, let's thank our speakers.
Thank you.
So let's move on to the next speaker.
Something is wrong?
Okay, great.
Okay, thank you.
Go ahead.
Okay, thank you, Chair. So, thanks our organizers for inviting me such a good conference. Actually, I enjoyed it very much. So, today I'd like to introduce slightly different topics. So, we are we have a plan to have a heavy ion experiment at JPAC. So today I'd like to introduce this project. Okay, so as you already know, so heavy ion collisions are new tool for Strange's physics. Actually, so this plot is already shown by Professor Onishi. So this is a directed flow, which is a kind of measured value for heavy physics. So as a function of rapidity. And so Professor Onishi pointed out, so that data point can tell us the interaction between hyperons. So this is a good example. So we have a very good opportunity to study hyperon interaction in using heavy ion collisions. So we can measure flow, or we can measure two-particle correlation. And also, we can produce a Strange component system using heavy ion collisions, such as hypernuclei or strange jet or dibaryons. Goals. So at JPAC energy, so we can expect efficient production of strangeness. So this is the left plot shows the measured K plus pi plus ratio as a function of beam energy. collision center of mass. So at JPAC energy, we can expect the very high ratio between K plus pi plus. So it means so we can expect the efficient strangeness production. And also, this plot shows the hyperon yield, hypernuclear yield as a function of collision energies. So this calculation is performed using a statistical model, and the calculation tells us so we can expect very large yield for hypernuclei. So for study of hypernucleus or hyperon interactions, so we can use this kind of heavy ion collisions. And also, we are interested in the direct study of high density matters. So this is calculated temperature and density map. So this red line shows the average trajectory of the average trajectory of this collision, and this purple point shows the maximum density in an event. So we can achieve 7 times larger density than normal nuclear density. So using this collision, this kind of collision, so we can search for QCD phase structure, study QCD phase structure. So first of the transition, Dirac superconductivity, and we can study the properties of dense matter. So EOS, direct study of EOS or something like that. And those current symmetrization can be expected. So for these physics topics, so we are planning to have a JPAC heavy ion project. So the main physics topics are following. So study of strange system and hyper interactions, and study of QCD phase structure in high density region. And so we are planning to have heavy ion beam, following heavy ion beams. So beam energy is 2 to 5 GeV, and we can accelerate up to uranium, and we will have maximum beam intensity of 10 to the 11th Hertz. So to have such beam at JPAC, so we need some facility upgrade like this. So the good point is, so we can use the existing accelerators. So we need new heavy ion injectors at here, so LINAC and boosters. And also we need a new experimental area and a spectrometer here. So actually, so it costs some money. So we are planning to have a staging plan. So at this moment, we have the ongoing PA collision experiment. So the main physics topics of the ongoing experiment is vector meson measurement in E plus E minus decay modes. In addition, so we will upgrade this spectrometer, existing spectrometer, for hadron measurement, and so we will take pilot data for heavy ion physics. So this should be done in a few years. And next, so we are planning to have new LINAC and reuse of KKPS boosters, and upgrade of this existing spectrometer to fit the heavy ion physics and heavy ion experiment. But so for this phase, so we can only have 10 to the 8th Hertz for gold collisions. And finally, so we can have the new booster and the new spectrometer, and so we can get final configuration, and we have large maximum beam intensities. So this is phase 1 booster ring and heavy ion LINAC, and phase 2 heavy ion booster rings. So this is already used very old one, and it is located at KK. Okay. So I would like to show some details of this staging plan. So first, I'd like to introduce the ongoing experiment. So we are performing an experiment to measure vector meson mass spectrum in PA collisions. So the physics is a modification of the spectra due to chiral symmetry recitation in the nucleus. So please see Gubler-san talk for detailed physics. So reaction is following. So we have a proton beam and so nucleus target and generate vector mesons and detect a plus E minus decays and reconstruct the mass spectrum of this vector meson. So this is a photograph of experimental area. So a primary beamline here is already constructed, and the beamline can be used as a heavy beams. And a new spectrometer is constructed. So this is dedicated spectrometer for measurement of E plus E minus decays, but we can upgrade this spectrometer for further hadron measurement and heavier physics. Okay. And I briefly show the status of the experiment. So this experiment. So first beam is held on May 24th, 2020. And the commissioning runs are performed in 2020 and 2021. So all detector triggers are worked well, and detector performance in commissioning data are evaluated. So this shows the target profile and the electron identification counters performance. So this blue line shows the electron peak. And also momentum reconstruction is also well done. So, and we can see the K-shot peak around here. Okay. And so we will take physics data in the next year, sorry. And then, so heavy ion physics experiment. So for phase ion experiment, so we need to upgrade the spectrometer. So physics goal of phase one experiment is following. So hadron interaction in dense medium and such a Cook phase. So we will measure flow to particle region and dielectrons. So and we will have heavy ion beams with limited intensity. So and so we need following upgrade. So hadron measurement and additional detector in forward region. So this is a schematic view of the spectrometer, the current spectrometer. So we constructed this part, but we need additional red colored part, the time flight and for the additional detectors. Then so we can extend the hadron measurement capabilities. So using the current detector setup, so the rapidity coverage is very limited. But so after upgrade, so we can have the almost full coverage for rapidities. And we can have the particle identification for hadrons. Okay. So, and then this is final spectrometer design. So it is still under discussion, but so we are planning to have large acceptance and low PT tracking detector. So then, so we can measure higher order flow or fluctuation or charmed hadrons. And so current plan is following. So we have hadron spectrometer, dipole plus TPC, and large acceptance. So we can measure large acceptance. We can have large acceptance for correlation and fluctuation. And so for study of hypernucleus, so we will have hypernucleus spectrometer. So using this hadron spectrometer and plus this sweeping magnet. Okay. This is a schematic view of hypernuclear spectrometer. So this part is for hadron spectrometer, and this part is sweeping magnet. So then, so this is a schematic view of hadron spectrometer. So this is dipole and TPC. So then, so we almost we can have almost 4 pi acceptance, and so very good particle identification. So we need a triggerless DAQ and high-rate counting. Enhanced physics capability for rare event fluctuation higher order flows, so we will have such kind of hadron spectrometer and high intensity beam. Okay. And this is a hypernuclear spectrometer. So this shows a closed geometry and sweeping magnet and collimators. So we limit the acceptance to beam trajectory. So then we can select the hypernuclear very effectively. So then even we have very high interaction rate, but the measured hypernucleus is a kind of reasonable rate. So this is the sweeping magnet, and so the generated hypernucleus is bended, and so we can measure the hypernucleus so in the suitable horizontal positions. Okay. And so we can use this TPC for measuring the decay products. So this is an example of expected result for hypertriton. So if this hypertriton is generated, so then we can tag the pi minus b, pi minus decayed pi minus, and identify the fragment by this Z and PZ plot. So this shows that we can tag this pi particle, pi meson. And also, we can identify the fragment in the ID in TPC, so like this. So then we reconstructed this pi minus helium-3. Then we can see this hypertriton. So this is a kind of performance plot. So we are now discussing and designing the final stage, final spectrometer. Okay. So I'd like to summarize my talk. So future heavy ion experiment at JPAC are planned to study strange physics and high-density matters. So significant facility upgrades are required for heavy ion experiment. We need LINAC and booster for heavy ion acceleration, and a new spectrometer and a new experimental area. So staging approach is under discussion, and first we can start with minimum upgrades based on existing accelerator equipment and direct spectrometer. Then we are planning to have full upgrades. So detailed design of detector configurations for each stage will be finished in a year, and the project proposal will be submitted to the JPAC. Okay, thank you.
Thank you for the overview for the heavy ion collision program.
Thank you for a nice talk. If I understand you well, you plan to upgrade your existing dielectron spectrometer, dielectron, yeah? So it means that you assume that you will measure also dielectrons with heavy ions. Is that right?
Sorry.
Will you assume that you will use also dielectrons in this future heavy ion experiment?
Yes. So, actually, so with this low intensity mode, so we can use this dielectron. But so high intensity mode, so this detectors cannot cope with that high entity rate. So at that point, so we are planning to have muon spectrometer.
Thank you.
I mean,
Other questions?
I think it was the slide 2, I think. No, well, basically the question is, can you go to about 4 then?
4.
That one, yes. You are expecting a very high density achieved to be at your beam energies. My question is, how did you estimate this high density? I am asking because we calculated or simulated collisions at about 800 MeV per particle, and the highest density we could get was about 2.5 nuclear saturation density. So what you did to get these high densities?
Yeah, okay, so this is a simulation result using JAM2 calculation. So JAM2 is a kind of hadron transport model.
Yes.
So, yeah, actually, so I'm not sure so about the detail of the calculation. But so, according to this model, so, and actually, so this is a maximum density in the event. So we have several kind of events. So kind of peripheral collision and central collision. So this event is for central collision. So
Yes.
for minimum bias, just total integrated collision. So we, the average density should be like 3 or 4 or something like that.
Okay. I think it would be very good to check this number.
Yeah.
Okay. Let's do one more.
Maybe he has a comment.
I'd like to make a comment on Irina's comment, and in the JAM2, then the way you run just a event generator based on the hadronic transport model. And in this figure, I guess that we do not include the Meefield effects, repulsive Meefield effects. Therefore, the higher density is also produced. And what happens when we include the equation we state, and what is the maximum density achieved on average and by the fluctuations is, of course, a problem to be studied. And Gunji-san, Professor Gunji, is studying hard to search for some kind of observables which reflect the highest density achieved in each event. That is the situation.
Yeah, I think so. The measurement is also important.
Okay, we need to move on. Let's thank our speaker again. So let's move on to the next. Okay, another JPEG program. Go ahead.
Okay, thank you, Chairman. So first of all, I'd like to thank the organizer for giving me a great chance to show our extension project at the JPAC Hadron Experimental Facility. I'm Fuminori Sakuma from RIKEN, and speaking on the behalf of the Hadron Hall Extension Task Force. Okay, so this project is actually has been defined with the community with and the facility side, and especially so many support of your community, our community, so the hypernuclear community is very helpful and very Thank you very much. Okay. So okay. Next. Here. I'm sorry. どれが Sorry. Okay, so at last, last month, our extension project was selected as the top priority project at the KKPIP 2022. So this PIP means the project implementation plan at KK, so the KK midterm plan. Okay, thank you very much. So I'd like to show the overview of this extension project today. So let me first from the big picture of the Hadron Hall Experimental Facility program. So so we are aiming to explore the origin and evolution of matter from the three Z's perspective, okay? From the elementary physics to the nuclear physics. So in the flavor physics, so there we aim to explore the mystery of the matter-antimatter symmetry, that is the matter-dominated universe, so using kaon, rare decay, and a mu conversion experiment. Okay, and next hadron physics. So there we aim to investigate the origin of matter creation. So that is the formation of the hadron from the quarks. So there we perform the hadron spectroscopy and a meson in nuclear experiment at J-PARC. Okay? So here. So in the strange nuclear physics, so many discussion at this conference. So there we aim to elucidate the matter in extreme conditions, such as the dense matter in the neutron star. Okay? So there we perform the hadron hyperon nucleon scattering experiment and the hypernuclear spectroscopy at J-PARC. Okay? So these three core lines programs have been promoted by using world highest secondary beam available at the J-PARC Hadron Experimental Facility. Okay? So the J-PARC Hadron Experimental Facility is a unique facility, so where we can conduct a comprehensive study from elementary particle to the high density hadronic matter physics. Okay? And this is the introduction. And here, this is the present Hadron Experimental Facility. Okay? So the primary 30 GeV proton beam is delivered to the T1 target, okay? And produced secondary beam delivered to the each beam line here. So that we have two secondary beam line. One is the charged beam line shared by two experimental area, and one another neutral beam line for the KL study, okay? So they are recently. So primary 30 GeV proton beam line was constructed in the 2020 year, okay? And in addition, so the muon beam line for the mu conversion experiment will be starting the next year. Okay? So this is a present Hadron Hall, and at the secondary beam line here, so that there are many achievements so far. So this is a summary of the achievement in the research, okay, at the Hadron Experimental Facility, present Hadron Experimental Facility. So in the flavor physics, so the K-long to Pizer-Newton bar experiment, such Pizer-Newton bar decay search has been performed the Koto experiment. So the measurement is now approaching the standard model of sensitivity for the CP violation. Okay? And the hadron physics, so the observation of the exotic hadron bound system, including K- meson, was reported. Okay? So this result established a new direction to understand the meson baryon interaction like this. Here is the K-PP bound state observed. Okay? And in the strangeness physics, there has been a lot of progress, okay, in the hypernuclear research. So we clarified the attractive S-2 Guza interaction and the deepened S-1 lambda and sigma interactions like this, okay? So at this conference, so many results were reported and discussed like this here, okay? Then, so here is the future research direction, near future, okay? So in the flavor physics, so search for the mu-e conversion will be performed by the COMET experiment in next year, from next year. So they search for the charge lepton flavor violation here using such a solenoid magnet spectrometer. Okay? And in the hadron physics, as the previous speaker Ozawa-san described, so the measurement of the spectral modification phi meson in nuclei will be has been performed from the 2020. Okay? And so they investigate the mass generation mechanism of the hadrons using a large spectrometer here. Okay? And the strangeness nuclear physics, so there we will concentrate the high resolution spectroscopic study of the S equal -2 Guzai hypernuclei as Gogami-san discussed on previous. Okay? So this experiment will start next year. Okay? This is a flagship experiment at the current experimental facility. Okay? So by systematic measurement of such a cascade hypernuclei or the double lambda hypernuclei, so that we can provide the accurate and systematic information on the Guzai-N and the lambda-lambda interaction, okay, using a S2S spectrometer, large spectrometer, which is now constructed. So the details of the experimental program using S2S spectrometer discussed here. Okay. So beyond that, so that we need a further research at JPAC. So in the flavor physics, so we need a further K-long to Pi0 universe search with a further sensitivity beyond the standard model, okay, sensitivity. And in the hadron physics, so the CHARM and the multi-strange baryon spectroscopic study is needed to establish a dicoin baryon to understand to connect their normal nuclei to the high density matter. So it's a key of the configuration of the dichrome. Okay? In the strange nuclear physics, so Nue-san already introduced, so that we need the ultra precise spectral study of the S equal -1 hypernuclei, lambda hypernuclei, with a cutting edge spectrometer. So to extract density dependent of the lambda interaction. So all present and all future program directed to the here. So they're in the flavor physics to further explore the new physics, and in the hadron physics, so that to understand how quarks build hadrons, okay? And in the strange nuclear physics, so we discussed how to elucidate the nature of the extreme dense matter, such as neutron star matter, okay? But however, so that we need more beam line and to extend our hole. So because we have limited beam line and no space to the extended beam line and physics. Okay? So there we have proposed the extension plan. Okay? Here is the current and here is the extended hole. Okay? So we will construct 4 new beam line from a new target system here, T2, and we will add a new operational function to the 2 existing beam line here. So by this extension project, we can expand the research programs, okay, to explore the origin and evolution of matter more and more deeply. So this is our extension plan, project, okay? Then here is the close-up view of the extension part here. So they are here, so to extract their density-dependent lambda interaction, so we perform the ultra-high resolution lambda hypernuclei spectroscopy at KHIHR beam line. So they are by introduced by the Tamura-san and Nue-san, okay, Nakamura-san. So and also, so that we perform the systematic lambda scattering measurement at the K1.1 beam line, okay? Then this detailed program was discussed at Miya-san. Okay. So in the hadron physics, so we are aiming to investigate our diquark baryon by using a high resolution charm baryon spectroscopy, here Pi20 newly modified beam line. And also we proceed the high resolution multi-strange baryon spectroscopy using high momentum and the high intensity separated K-on beam line, K10. K10 means up to the 10 GeV can be used available. Okay. So finally, so in the flavor physics, so we aim to search for new physics beyond the standard model from the highest sensitive K-long to Poisson universe measurement at K2 beam line. Okay. So here is the research program, the flagship program. Okay. So next I show quickly the overview of such a flagship experiment. Okay, in the strangeless nuclear physics, so we aim to solve the hyperon puzzle, as discussed a lot in this conference. Okay, so the important keys are lambda NN3 baryon force. Okay, as you know. So we need to determine the tiny fraction of the 3 baryon force effect here. So of course, as you know, so the lambda binding energy of heavy lambda hypernuclei give us the density-dependent lambda interaction. So we need precise measurement of the heavy lambda hypernuclei at around the saturation density here. Okay. Then, so we have one sample of the past measurement of heavy hypernuclei, red hypernuclei. Okay. So you can see we have no sufficient resolution and here, so that we cannot determine the precisely the binding energy. Okay. Thus, we need the separation of the lambda orbital state very clearly, like this here. Okay. By doing such an experiment, so that we can deduce and obtain the precise binding energy for each orbital state, and which we depend on the density of the state. Okay. So at J-Park experimental facility extension, so we realize such a measurement using the HI-HR beamline. Okay. So this beamline adapted dispersion matching beamline technique in the GeV energy first time. Okay. So here is a schematic view of beamline, and we can perform the pi plus k plus reaction measurement, and will be obtained such a huge, quite nice spectrum. Okay. So we will break through the resolution limit compared to the past experiment, namely the better than the 0.4 MeV or so. Okay. So by combining their very precise data of the lambda binding energy obtained at the HI-HR beamline, okay, and so the two-body lambda interaction in the free space from the lambda and scattering measurement, systematic scattering measurement at K1.1, then the density-dependent lambda interaction will be deduced, extracted. So we can go forward to the understanding of neutron stars more clearly. I think we hope. Okay. Okay. So next is the hadron physics. So in the hadron physics, so we investigated diquark in baryon, so which is a starting point toward the understanding of the dense quark matter. Okay. So we perform the charm baryon spectroscopy with an intense high momentum pion beam available at the high P pi 20 beam line. Okay. So here is a charm baryon lambda sister, and this system composed of the heavy charm quark and light UD quark. Okay. Then this is a diquark here. So the internal motion of this system is should be governed by this two light quark. So this is a diquark. Okay. Then, so we will establish a diquark by disentangling these two quark motion here, rho mode and lambda mode. Okay. So here is the expected spectrum of the pi minus d star minus spectrum, missing mass spectrum here, so that we can clearly identify. We will clearly identify that such a higher state of the lambda c star. Okay. Then, so that we can measure, obtain the production rate, namely the total cross section from the missing mass spectroscopy, And also, so we can obtain the decay information from, by reconstructing all decay particles. Then we can measure their spin and parity information. Then we will provide the information on die quark in the baryon charm quark. Okay? Then next, we expand this die quark study to the strangeness sector. So that we will merge strange baryon spectroscopy with the intense high momentum separated K-on-B at K10 beamline. So here, so we will measure the cascade star and the omega star baryons to study the die quark in different systems systematically here. Then, so systematic measurement of charm and multi-strangeness baryon will reveal the internal structure of the baryon through the die quark. So this is a hadron physics, okay? And finally, so here is a flavor physics. So the extended facility, so that the COTO step 2 experiment will be performed to search for the rare K-on decay of the K long to the pi 0 nu bar beyond the standard model sensitivity. Okay? So this decay channel is one of the best probe for the new physics search. So they are at the present hadron experimental facility. The COTO experiment is running, and this their measurement is approaching to the standard model sensitivity here, and will be achieved there in a few years or so. However, so this sensitivity will be saturated gradually, so that we need a new experimental program as a COTO step 2. This COTO step 2 experiment aims to search for this rare decay beyond the standard model sensitivity, about 100 times over. So this experiment used the intense neutral K-on beam at KL2 beamline by changing the extraction angle here, and construct a large ultra-high sensitive detector here. By using this apparatus, so the new physics search with the world highest sensitivity will be performed with a more than 100 times sensitivity. So this is a COTO step 2 experiment. Okay. So I show the status and timeline of the project. So, okay, here is the present status. So this project has been listed as one of the candidate projects to be funded by government for the long time, about 10 years. So at last, so the last month, this project was selected as the top priority project to be budgeted in the KK midterm plan. Financial year 2022 to 26, okay, at the KKPIP 2022, so project implementation plan. So the result will be published soon, this page, okay? And also our project is, of course, ongoing. So the facility preparation status is summarized here, so all the preparation status is ongoing and well studied. Okay, someone is completed and someone is in progress. And so the project will start soon in full swing. Okay. And finally, this is the timeline of the project. So this project is a 6 years project. Okay. So the construction parallel to the beam operation in the first 3 years is possible. And, but however, we need a beam suspension in the next here, 2.5 years. Okay? So we will start the project if financial year 2024. So we have about 4 years before the suspension, so that we can perform and complete the present program at the current experimental facility. Okay? And also, so the COMET phase 1, so MUI conversion experiment will be finished. Okay? Then we move to the Hadron Hall extension shutdown to connect the present hall and expanded hall. So in around 2029 or so, so that we can start the expanded programs with more beam lines at JPAC. Okay? So this is summary. Okay, we have performed a unique research program both in the particle and nuclear physics at the High Intensity Frontier JPark. Okay? There, we conduct a world-leading research program in the field of the Schrödinger nuclear physics, hadron physics, and flavor physics. Okay? And this extension project was selected as a top priority project at KKPIP 2022. So the project will start in the next year, we hope. Stay tuned. Thank you.
Thank you so much for laying out the exciting JPark future plan. Any comments, any question? No? Oh.
Thank you very much for the very exciting presentation. So could you go back to the timeline of the construction? Yes, this one. So you have a 2.5 years somehow the suspension for the physics program from 2027 until the mid of 2029. And I suppose that there are a lot of students, there are lots of postdocs or young people working for this project, but they cannot take any data for this 2.5 years period. Do you have any plan to send those young people doing some physics program outside of JPark, like for example FAIR, because the FAIR is starting sort of the operation from 2027. So I think somehow it is somehow matching to your construction plan. So I just want to know if you consider this kind of a plan for the younger people or not.
Yeah, thank you for your comment and question. So there, especially it's a very, very important point. So there we need to keep or shorten this extension, suspension term. Okay, but before that, so we have many programs to be conducted at the present facility during this term. So we can take a large data. So their young people can analyze their data and enjoy the physics at this term. And such younger people go to this era, we think so.
So this means that you really want to keep those people
but we have many things to do. So for this extension program, so there detector development and for the young people.
The answer is by all means to keep them.
Okay, thank you very much.
So, thank you.
Thank you. Thank our speaker.
Thank you.
Okay, so let's move on to our final speaker. Professor Tamura gave us an overview for the progress, experimental part.
So now we are coming to the end of this very fantastic conference, and I'm not very sure I can give a good talk, but anyway, I will try to say something, not a summary talk, but and I want to express my really sincere gratitude to the organizers. Okay, anyway. I was told to talk about overview of this field, hypernuclear physics field, and the highlights from running experiments and perspectives. So when I listened to most of the talks here, and I but I found there are several very important subjects. One is hypertriton and NN lambda, and double strange hypernuclear system, and Wien scattering experiments, and femtoscopy, and also chaotic nucleus and chaotic nucleus system, and also future directions and facilities. And as I said, this is not a summary, and also I'm an experimentalist, so this talk will be made in terms of, from the viewpoint of experiments. So I can't cover all of them, of course. So I will cover, on the other hand, only some part of the plenary talks. So I have to say, I'm sorry in the beginning, but please let me start. So in the beginning, we have heard many talks about hypertriton. So I don't have to repeat this problem, but anyway, as you know, in the nuclear physics, the deuteron played very important role. In the same way, hypertriton should be extremely important because the smallest band system has, as I said, particular importance. We can test the two-body interaction precisely through the exact calculation. And as you know, this very small binding energy and lifetime, lifetime was not measured before very well, but many people, including me, believed this small binding energy and believed that the lifetime of hypertriton should be almost the same as the free lambda lifetime. But now we know such kind of very important object of nuclear system should be investigated more seriously, should have been investigated more seriously. So now high quality hypertriton data are must for our field, that we know that. But it was not seriously recognized before. So this importance was noticed, has been noticed since Hi-Fi group and also STAR reported much shorter lifetimes than the free lifetime of lambda in 2013. And I remember the previous HYPE conference, which we had in Sendai in Japan, 2015, Professor Tullio Bressani proposed to have topical session. And one of the topical session subject was the hypertriton lifetime. The other one was Wien scattering. And I feel very happy in this conference, these two has been a very important subject, and we could see good experimental data. And so this is just a list. I can't review one by one, I'm sorry. But there are so many experiments running, or they took data and gave some numbers of the new lifetimes and the binding energies and so on. But in principle, you know, these 1, 2, 3, 4 are heavy ion collision experiments. And you know, in STAR, now they are running with a lower energy beam energy scan. So the energy is lower, but ALICE is still running at a very high energy. But in both cases, the lifetimes and the binding energies are coming. And HADES also gave a new data of the lifetime. I don't know about binding energy. So this STAR data have been already published. Also this one, this old one. Oh, okay, this is the most old one. Old one means the data which was published just maybe after the previous HYPE conference, or around there. So this is only the new one after the previous HYPE conference. So you know, the lifetime of the hypertriton has become, okay, this is a previous one and this is a new one, and now it has become longer. But anyway, HADES also provided new data. And Saito-san's WASA experiment, WASA-FRS experiment has just taken data, so we can also see new results here. And anyway, these 4 experiments measures the decay length, not the time itself, the length of the track. And of course, for the binding energy, they need the invariant mass measurement. But on the other hand, you know, in order to understand such a very important quantity, we had better have a completely independent experiment using different technique or method. So different ones like this. One is the experiment which is running in JPark, at JPark, by K-pi0 reaction to directly produce hypertriton and measure the time difference of the production and decay. Ma-san talked about it. And also in MAMI, so-called decay pion spectroscopy is running, and it was successful for hydrogen for lambda lifetime. I'm sorry, binding energy. Okay, sorry, this is for the binding energy, not the lifetime. And in the same technique, they will run again with lithium target for hydrogen 3 lambda decay pion. So I hear that with a special calibration technique, they will achieve a very, very good accuracy of the binding energy. And also, Saito-san's group in RIKEN is now analyzing the emulsion data which was taken in previous JPark E07 experiment. And I hope they will provide many hypertriton events with precise lifetime and binding energy data. And also, as Nakamura-san said, in the next Jefferson Laboratory experiment, we run with a light target, helium-3 and helium-4, so that also the binding energy will be obtained. So maybe in this a few years or so, we will have various data with much, much better accuracy than before. So I think, I feel this so-called puzzle may be clearly solved, and we can achieve a much better understanding of the wine interaction. So, okay, this is just a list of this, the plot of the lifetimes. But anyway, we can say, we had to better wait a little bit more to see the other data from different methods. But I just want to say, I'm a little bit worrying about so-called psychological bias may come in, because here around the data points are rather, arranged this way, but now new data is systematically shifted, it looks to me. Of course, everybody is very experimentalist, very careful in removing such kind of psychological bias. But we, even though we should be very careful, yeah. Okay, anyway. And, okay, that's all, okay? So, binding energy is also important, but we need much more data. And we were surprised to hear this STAR result, but the new ALICE result shows a much shallower, much smaller binding energy. But even though we need more precise and independent data here. Okay. So I'm looking forward to hearing from MAMI for decay pion result and also emulsion analysis result. Okay, so I just want to mention a little bit about JPark experiment. This is completely different type, direct measurement of the production and decay time difference. And by using K- beam and just detecting pi naught, and with the helium target, helium-3 target, and the hydrogen-3 is produced, and by looking at this decay pion and measuring the timing of the pion. And this experiment was already tested with helium-4 target and observed very good hydrogen-4 lambda decay pion spectrum and also lifetime here. And the lifetime was obtained like this. So the experiment with the helium-3 target will run maybe next year. Yeah. Okay. So I also want to mention about new data from Jefferson Laboratory. Chairman talked about this very interesting spectrum of tritium target. So if there is a peak, it means the lambda NN bound state or resonance state. And so because of the statistics, it's not clear, but it seems to me something can be here or may not be here. And the chairman said the significance is 2.2 sigma. So of course we can't say, oh, we observed it, but it's a good chance. We have a rather large possibility to find it if we can repeat this experiment with much higher statistics. So I hope by the next HYPE conference, I want to see the final conclusion. So this is just at this threshold. Okay, it's very interesting. So I really want to mention about three-body hypernucleus level scheme of three-body hypernucleus system. It was shown by Ukai in my group in JPAC, and she said by measuring the gamma ray, possible gamma transition from the excited state, then we can, say much definite result on the unbound NN lambda or such excited state of hypertriton. So if this is bound, then this hypertriton, we shouldn't say hypertriton T equal 1 state can be bound and gamma ray can be observed, may be observed, because isospin is different and it can't decay into deuteron and lambda. And also, if this binding energy of hypertriton is deeper, then the upper state, it should be unbound. Everybody believes it's unbound, but it can be bound. Then we can see this gamma ray. So that we don't know, the probability of looking and of observing such kind of gamma ray may not be so high, but I don't know. It is anyway worth doing. This experiment is worth doing. And when but yesterday I received an email from Benjamin. He said, if we look at such kind of production rate of various fragment and hadrons in the heavy ion collision, all of them are very well fit by thermal model, even the hypertriton. So if this is bound, then it should have 3 times more yield compared to the ground state. So the yield should be higher than, this yield should not match with this expectation. So okay, anyway, we don't know, but it may not be bound. I don't know. Well, this is an interesting comment. Okay. So I will go to the double strange system. So Nakazawa-san showed us all these emulsion event taken in E07 experiment. And at present, we have 47. But now we found that many of them cannot be identified uniquely. So for single hypernucleus, identified events are only 2 here. And for twin hypernucleus, which shows the cascade band system, we found a little bit more, 1, 2, 3, 4, 5 and 6, including the previous KK experiment. So now, in order to improve the accuracy of the binding energy, they are now introducing the X-ray microscope to see the track, the grain of the emulsion track very clearly. And also, as I said, Saito-san is now in Riken together with Nakazawa-san, are trying to do so-called overall scanning with by introducing machine learning method. And it is very, it should be very, very helpful to find many, 1 order of magnitude or more many events. Then I just want to show you this. This is the most recent paper published from Nakazawa's group. And this is only for nitrogen 14 plus Xi minus event. But somehow this event seems to be well identified from the twin decay to the twin hypernuclear systems. And anyway, it seems we can see two clusters of events here and here. And then naively, this is assigned to the Xi P state and Xi S state. But this is, we have I have a caution. All of these theoretical predictions seems to say this is one state and this is 2p state. But these theoretical predictions are using already the old Brookhaven suggestion of about 15 MeV binding, this without any peak, but we can see some event excess to the bound region and saying about slightly deeper potential. So that then, so that all of these suggest that this is S state and this is P state. Okay, then it seems that all of these looks rather consistent. But anyway, we need more data. And one big problem is that, as Professor Gao commented, usually the Xi should not be absorbed, should be already absorbed at 3D orbit. And it never, in the usual sense, it never comes to the 1S state. And in the lattice QCD, recent lattice QCD calculation shows the sigma n lambda lambda coupling is one order or more smaller than we expected before. But even though this seems rather strange, so we need much more number of events and also theoretical works. So there are several theoretical works, but I'm sorry, I don't have a time to review them. Okay, but we are now in a very interesting position. Okay, so, and also we heard about Xi X-ray experiments, and it's a few experiments were already done, but even now the X-ray haven't been observed. We need more efforts. And also, as Gogami-san talked today, a new spectrometer will be launched soon in JPARC, and we can start such kind of K-K plus missing mass spectroscopy with very good resolution. So this will give us new data soon. Okay, so let's go to the next topic of Wien scattering. So all of us has been waiting for high quality Wien scattering data. And now a new era of studying hypernucleus from two-body Wien scattering data has come. So as you have seen many times, this is the new result at JPARC by Miwa-san's group, and showing the sigma minus proton elastic and inelastic scattering, as well as sigma plus proton elastic scattering differential cross section. And even in this case, the phase shift was derived. So this is the first data of the phase shift for Wien interaction. This is the first one. So anyway, this is very interesting result. And of course, in terms of the Cork-Pauli effect, this result may be very interesting. But anyway, such kind of experiment will continue more and more, not only sigma, but also lambda. And at the same time, also, from Jefferson Laboratory, the class group did an analysis of the lambda, which was produced by photon beam, and looking at this kaon and the scattered proton and decay of lambda. Then they found such kind of very high statistics cross-section. Okay, this is now just a total cross-section of lambda proton elastic scattering. Very interesting point is that this energy region is higher than JPAC. In JPAC, the energy region of sigma, okay, this is the case of sigma, but it is about 4 to 800 MeV over C. But in this case, the lambda momentum is higher than this. So it's very complementary. And also, this photon beam is polarized so that we can study the polarization observable given to lambda. And also, deuteron scattering data also exists, and analysis is going on. And I hear that by making the K-long beam lines, they can do Xi proton scattering in future. Okay, it's very, very interesting. So this is a comparison. As I said, JPAC, the hyperons are produced by pion beam. So that's why the momentum of hyperons are limited around here. And in the case of JLab, the hyperon momentum is higher. It's complementary. And also, in this case, by using hyperons, by producing hyperons with pion beam, we know the lambda has a very large 100% polarization. So we can study spin observables by using this lambda. In the case of JLab, the photon beam is polarized. It's also used for mechanism of hadron production. And I will, okay, so in the femtoscopy method, of course, it gives us a various hyperon, nucleon, or hyperon interaction data. And particularly, lambda or Xi cascade nucleon, or even Xi lambda or something like that. I mean, multi-strange systems that cannot be or not easily done by in JPAC or Jefferson Laboratory. So this is very unique and very important. And also, the momentum region is complementary. They are very strong in the getting the information of the interaction at very low energy. So these three methods are really complementary. So that now this experiment will grow up, and we can get much more, plenty of data until the next HYPE conference. So it will be very important to solve the hyperon puzzle. Okay, so femtoscopy. So I remember in the previous HYPE conference in Potomac, for the first time, I heard about femtoscopy result, and I was surprised very much. This was the Xi proton scattering, not scattering, the femtoscopy data. And now it has grown up to be a very big, how to say, business, field. And today, we saw many good presentations from very young people, particularly in Alice group. And I have no time to talk each of them, but in this way, now various different channels are analyzed, and all of them has now very high statistics, and I hear that the statistics will be much higher soon. And now this method, this femtoscopy method has established as a standard tool to study hadron-hadron interaction. So, and this is just, I just happened to find this list from this presentation, but it's surprising. Proton omega, or proton phi, or baryon bar, or proton B meson, or this lambda Xi, lambda cascade. Such kind of very exotic channel can be really measured. And also, three-body force can be also studied. It's very surprising to me. And okay, this is one slide from three-body force presentation by her. And yeah, okay, still maybe we need much more statistics and more careful, maybe theoretical treatment. But anyway, by studying these three particle correlation and subtracting the effect of the two-body correlation, then so-called, what to say, three-body cumulant can be obtained in this way. And okay, this is not very significant, but in the case of PPP, they observed a very big difference from, the evidence for three-body effect. So it will be very interesting in future. So, and theoretically, many people are also defining the treatment of this femtoscopic method. And several presentations was here, but for example, Kamiya-san's talk showed several interesting points. And one is how to treat the coupled channel. And by adding this term with weight factor with different source size and wave functions, and then in this way, the such coupled channel cusp can be really reproduced. Okay, this is the case for lambda xi and coupling, but in this case, the coupling is small, and at present we can't see. But this is very strong method and very interesting. And I was also surprised to hear this presentation. Okay, this is from STAR, not Alice. Because even k-on correlation, they can say something about final state interaction. K0 meson resonance. And I don't understand the details, but in this way, now we can use this method to study the such very broad meson resonance as a final state interaction of these pions or kaons and so on. Yeah, it's really interesting possibility. So, okay, then I come to the k-on nuclear system, k-1 nuclear systems, and I have no time anymore, so that this is just a copy of the Otton's presentation today. Yeah, it was really good. He made a very good review, so I just put it here. But I just want to mention a little bit about this JPAC experiment. So this E15 result with about 50 MeV, 40 MeV binding structure is theoretically well interpreted as K by N state. And this just appeared in the previous HYPE conference and then published. So now, okay, so now it was very well analyzed and published another paper by Yamaga-san. And then I also was very surprised to hear in Hashimoto-san's talk, similar spectrum appeared, but this is helium-4, not helium-3. So that this should be, this peak should be lambda due, no, k-on in state. Yeah. Of course, this data was taken as a test experiment for different experiments, a test beam time for different experiments. So if they use much more beam time, then they can clearly determine the depth of, the binding energy and width of this system. So in this way, this chaotic nucleus has become now a stage of the systematic study going to heavier systems. And also they are going to determine the spin parity. And they have just started making a bigger spectrometer to see such a lambda proton or deuteron decay product. Okay. Then today I also heard about chaonic X-ray business from Johan. And so Shidata 2 is now challenging to chaonic deuteron. This is very difficult experiment. But at the same time, I hear this result and it's also surprising. This is not the experiment using so-called silicon drift detector, I'm sorry, SDD, sorry. But in this experiment, they used a newly developed so-called transition age sensor of the superconductor, TES, as a sensor, as a detector of the X-ray, and then it gives 1 order of magnitude better resolution. So the shift and width accuracy is surprising. It's really surprising. So this is the first case that this detector was used for such high energy beam experiment. But if we can use it for various different exotic atom experiments, then it will change the world. Yeah, it's very exciting. And also, which one? And also I had some new result from Amadeus group. They are, studying the low energy kaon nucleon interaction to see the kaon proton scattering amplitude below the threshold. And sorry, I had no time and I couldn't explain you well, but some new data appeared, and it's very encouraging to make the kaon nucleon interaction. And so I'm sorry, I can't review the theoretical achievements by using such new data. But anyway, Hyodo-san said, now the two-pole structure of K1.5 is now accepted to particular data group, and now we can see these two poles, two resonances in PDG. So now, and also, I'm happy to hear that the femtoscopy result of proton kaon also make such kind of experimental points to the KP scattering amplitude, KP scattering, okay? So finally, I'll shortly mention about facilities and some future directions. And so I'm sorry, I can't review the GLUX report today. But anyway, in JLab, not only Hall A, and of course Hall B, I'm sorry, I couldn't write this way, but Hall B is also, class is also doing the scattering experiment, scattering data, and the GLUX joined. So now in JLab, in all the halls, strangeness, nuclear physics and hadron physics are going on. And also in GSI, Hades and also WASA FRS working for kaonic and hypernuclear experiment. And also in Daphne, the Amadeus and Shidata group are working intensively. And there are many experiments in JPark and future plans are running. And also, I can't write here, but anyway, ALICE and STAR data are really important for femtoscopy. And also today, I didn't mention, but also there were several exotic hadron study report of the hadron analysis from Bell experiments at BESS in China and LHCb and so on. So they are also important for future. Okay, anyway, then I only talk about this JPark project, and I was, thanks to the organizers, I made a topical session for this, and also today we heard from Sakuma-san about details of this project. So here, as I said, these two beam lines will be used for strangeness nuclear physics in order to solve the Hyperon puzzle. So I need your theoretical collaboration and support. And I can't summarize here, but there are many theoretical talks related to this project. Yeah, of course. The Hyperon puzzle itself is, of course, very important. And also, baryon-baryon interaction model should be studied. And then nuclear structure calculation is also really important. And we need such kind of various types of theoretical works combined together. And I just put finally the summary page of Wolfram Weise, and it says he is supporting this our project of measuring high resolution spectrum of lambda hypernuclei, as well as determining two-body wine interactions by scattering experiment. So, but after this project is realized, we want to go to the next further forward step. This is JPAC heavy ion project. It was reported by Ozawa-san today. So by introducing injectors here, it's not cheap, but not impossible price. And then, and also construct some detectors here. Then we can study. Of course, the main, most important subject is to directly create the very high density matter, which may be going beyond the phase transition to the Korg matter. But another important thing is to see the directed flow of lambda. It was pointed out by Onishi-san in this conference. Then we have a chance to see the effect, see the lambda's binding energy at higher density matter, inside higher density matter. Of course, we can see also find several new types of exotic hypernuclei and hadrons and so on. Okay, so I hope we also want to continue our activities to this way in JPAC. Okay, thank you very much. And as I said, now more and more our close collaboration between theorists and experimentalists, I don't know which is which, but, and also between different facilities, including very high energy experimenting LHC or some other groups in the world, should be combined and collaborate with each other. That's more and more important. So finally, I want to thank the organizers, because this conference was really wonderful, very successful. And the program, and also this fantastic location, and the perfect organization, and also this hybrid style worked very well, I think. Yeah, it was really good. And also social events were really wonderful, yeah? So we sincerely thank the organizers for their very great effort to realize such a fantastic 3D conference during very, very difficult time of COVID. So actually, this is my first attendance to the 3D conference after COVID comes. So maybe many of you are the same. So I'm very happy now, and I want to say thank you very much. So finally, we had a can I say this? No. Not yet? Not yet. Not yet? Not decided? It's my privilege. Okay, you should do it. Okay. All right. So thank you very much. Yes.
Okay, thanks for Professor Tamura gave such an experimental summary. And personally, I also feel the organizing committee, Professor, Jury, your colleagues really did a fantastic job. We really enjoyed, and I believe that all the participants enjoyed, and such a large audience. And this conference experience will be remembered for a long time. Such a special. Hopefully, next conference, we will see more young audience, more young guys. That is important. So let me pass this to the organizer. And let's all thank our organizer again.
Thank you very much.
As you see, I did not expect your thanks. So I prepared a short speech here. So thank you very much for your thanks. The members of the local organizing committee are not the only one who deserves credit for this conference. There are three important aspects in the game. And the first one is the place, the setting. And of course, it's quite easy to organize attractive meeting in the stage scene, which is made by Prague. Then the other important aspect is, time. Because after 2.5 years of starving due to COVID-19, we finally got a chance and meet here, and so we hungered very much for meeting again in person in 3 dimensions, as Hiro said before. And the third and very important aspect is, or are the actors, because this is the crucial ingredient that makes successful any meeting, that makes success of any meeting. And so thank you having you here because you are really a fantastic team during this week. Then finally, I would like to thank the guys who were sitting over there by the table, these 3 guys who help us a lot with audio and video during the conference and with these online presentations. So many thanks to you. Then I would like to thank to our conference secretary from the AMCA company, Mrs. Eva Uhrová. Please come here. Then I would like to thank the manager of the hotel, Eva Grimová, who is unfortunately not here, but she is also far here. Don't worry, I will give it to her. And if I won't see her, I will bring it to my wife. So it won't be lost. And the third thank comes to one important member of the committee, local organizing committee, Jarka, who helped us. Please come here. Thank you. And this way I expressed thanks of our Japanese colleagues for PCR testing yesterday. And now I will have a few announcements before we go for lunch. The first one is that the proceedings of the conference will be published, as you heard, will be published as open access in the European Physics Journal web of conferences, and we will provide the authors of the contributions with the details during next few days. Then I would like to ask participants who were yesterday at the concert and who made photos there, if they can send it to me, because we would like to put some photos on our conference website. And there you will find also photos made by our photographer, Dalibor Skopil, member of the local organizing committee, and also the conference photo in few days, maybe during the weekend or within 1 week. And finally, now please be prepared, not yet. I would like to announce the place of the next 15th International Conference on Hypernuclei and Strange Particle Physics. So the next conference will be in Japan in 2025. And I am really very happy to pass the torch to the next chairman of the conference, Tunue Nakamura. And the last sentence, I promise. Thank you again for coming to Prague, for taking part in person as well as online in the Hypernuclear 2022 conference. And we all look forward to the next conference in 1995 in Japan. Thank you again, and goodbye.